Hey, welcome. Do it here. Finally here on part 10 out of 10 of my Philosophy of Science series. Almost a year later. Um, it's been a good journey, and to a large extent, the journey has just started. A lot of information, a lot of stuff to cover, and a lot of this we just scratched the surface of. So, today I'm going to cover a few peripherally related topics to the philosophy of science, mainly the mind brain identity theory, the philosophy of statistics, and computational philosophy. And that will bring to the conclusion my philosophy of science series. I'll probably still continue with some similar things on week in review, and definitely go much more in depth. In fact, if anyone has been watching week in review, I have went much more in depth into a lot of these same topics. So, this was due diligence of an interesting topic. I learned a lot. I gained a lot from this, and there's a lot more to cover. So, I'm going to do a review of all 10 parts, what we did cover over the last year, and I'll make some comments on that. And then I'm going to read three more articles. Might take about 3 hours. So, like relative to these marathon streams, 5, 6, 7 hours. Today's stream might only be 4 or 5 hours, depending on how much I ramble. And then, after I conclude some thoughts on the series, I'll lead into the next series, which will be metaphysics. And to some extent, metaphysics should have came before the philosophy of science. And I've mentioned on earlier streams about the philosophy of science, similar to one of the very first series I did. In fact, the second series I did was Mesilas Yesharim, the Hebrew text, the path of the righteous, was a lot of things of righteousness are so simple that the people who talk about them emphasize that are assumed to be simple, and that everyone thinks they understand these things. But in reality, there could be quite complicated. There could be quite a bit of significance or complexity behind it. And at the level that they're so simple, they're easy to forget, or they're easy to not appreciate the implications of it, or just to think that they're widely known and accepted. So without knowing the disputes or the importance of this. So the philosophy of science is probably one of the least understood, well appreciated areas of modern day philosophy and science, although there might be wide assumption that people do understand it. And so I covered the Vienna Circle in depth, the history, uh, from Newton and Hume and Hobbes, and the beginning of empiricism and the Royal Society, through Kant and the Neo-Kantians, and the Vienna Circle and scientific realism, logical positivism, to the branches today of largely materialism. And we'll close the chapter on materialism with the mind brain identity theory, which will lead into the metaphysics, with the presumption of most scientists today is that consciousness derives from brain functions. And so one of the main reasons why I did this series was to push back against the idea that consciousness derives from the brain. And for the multiple truth hypothesis. And so people mostly believe that it's just well known and explained how consciousness derives from the brain, and materialism in general. So too that people who believe in spirituality and the soul are thought to be dumb. Ace Royally, God bless Shalom. That outside of religious circles, say like um, anyone wearing a yarmulke, could be seen to be anybody having religious leanings is thought to be naive, uninformed, uneducated. In the small circles of religious people, or like maybe across America, Protestant evangelicals, other places of the world, it could be the opposite, and there might be more skepticism towards science. However, this general trend that there is broad skepticism of spirituality, and most of it is based upon science and conceptual, like scientific realism, and what I covered in depth with the Vienna Circle, and especially in Week in Review, is the metaphysics position that ended up deriving from the Vienna Circle and Rudolf Carnap, and led to modern day logical positivism and scientific realism, where people believe that metaphysics is either solved or unimportant. And Duvid's more leaning as a metaphysician. So that was the idea why I did the series. Um, when I was still streaming with Church of Entropy, and we had all these definitional regresses. What do we know? What do we don't know? And what's the fine dividing line between science and metaphysics? And generally, metaphysics is giving concepts about things that can't be empirically tested, that are beyond the senses, as opposed to science, which is in the realm of empiricism and tested. And on Week in Review last summer, I did in depth the various deep dive into truth, which I didn't cover that much in the philosophy of science, like the correspondence theory of truth, the coherence theory of truth, pragmatism, although we've talked a little bit about pragmatism, but as a compendium to Week in Review, where we have covered a lot of these topics more in depth and more names. So almost all of this series has just been the Stanford Plato Encyclopedia of me highlighting, reading articles, and doing the due diligence. Like, what's the current state of knowledge? Who are the main names and ideas? So if anyone else found this series interesting, I hope you did. Glad to be of service. Few people, discussion, maybe more mystically leaning, maybe like active inference. I could eventually get more involved in some sort of discussion group. It's not widely appreciated, these topics. So, one of the reasons the delayed why it took me a whole year to do it was because I don't have anyone to talk about this with. So I'm just rambling into the camera, and people watch my videos. Like, I see, some people watch my videos, give me feedback, a few comments in the chat, but very few people know about this stuff or even care about it. Like my dad the other day, we were eating lunch, and just a few brief minutes, asked me what I was up to, and I was mentioning some of the stuff about the Vienna Circle, and even that, like, very few people are interested in this. Like, just to have a small conversation about, like, oh, isn't this interesting? What are you thinking about? And you're like, well, I'm studying logical positivism, the Vienna Circle. Maybe in like University of Michigan, like if you join like a math club or a philosophy club, there would be a handful of people that would be interested. I don't know. Like, I just put these videos out there. There's not that many videos. Like, because as I've been studying this stuff, I've searched, all over the internet, YouTube, for videos. There's articles written on this stuff, and most of the articles written on this are published in the journals of the handful of students of the Vienna Circle that successfully set up philosophy of science departments. And even Stanford, the encyclopedia, the Plato Stanford Encyclopedia, is a derivative of the Vienna Circle. And so I feel good about having read through these things, done the due diligence, knowing a lot of the various ideas, and that I basically, over a year, 10 videos, 50 hours, covered the major topics in the philosophy of science, a complete introduction to the major issues, some of them quite a bit more in depth. There's a little more. I can't say, it's impossible to cover everything. And a lot of these issues need to be handled much more in depth. And, certain level, like, you actually have to get to the science and the symbolic notation logic. So looking, some more of this up, even the last week, some this week, you'll get into notational representation, where, well, science is not properly represented in language. You can't really talk about science. Science has to be given formal symbolic representation, and it takes quite a bit of training to be able to understand logical symbolic representation form of scientific theories, to just look at papers that largely have symbolic logical notation. And but that's what it takes if you really want to understand it. And to some aspect, you can understand quite a bit about the philosophy of science without necessarily being a heavy scientist, like having an advanced degree in science or mathematics. Although, to a large extent, certain logical, not just like logic to think logically, but symbolic logic, mathematical logic, is one of the prerequisites also for the philosophy of science. So you can understand a little bit without having taken formal logic, but at the advanced levels of the philosophy of science is properly represented in a formal symbolic logic. So, with that, let's jump right in and review what we covered. So, here's the series. See, 10 parts. The first part was in 10 months ago, March 19th, almost a year ago. So the very first one, I did some Wikipedia, overview. I talked about historiography in science, the history of science, internalism and externalism, the internalist view of science versus the externalist view of science, where internalism is just saying that science progresses purely based on the ideas and advancing off the ideas, as where externalism looks at science as occurring within a place and time and having cultural influence. And I talked on Week in Review, or a little last week, you see like inevitabilism and Pickering, and the concept of how much of science is a cultural construct as opposed to inevitable in like actually moving towards a various direction. And we talked about the history of the scientific method. What is the scientific method? How did the scientific method come about? Got straight into Thomas Kuhn's The Structure of Scientific Revolution, which is probably the best known work on in the philosophy of science and how science progresses. So if anyone's heard about the philosophy of science, like a non-expert, one of the most common things people heard, the best-selling author is Thomas Kuhn's The Structure of Scientific Revolution. In fact, I had read that book in high school. There's a few others like Ayers from the Vienna Circle in England, and like before World War II even had written a popular book. Karl Popper. But I think Thomas Kuhn's Structure of Scientific Revolutions is the most widely known publication and thing that people know within the philosophy of science, although within the philosophy of science, Kuhn is not even necessarily that big of a player. And then we looked at Hobbes' precursors to the philosophy of science, where I believe that Hobbes was not a formal member of the Vienna Circle, and Hobbes didn't know mathematics and logic, but he had some level on the beginning of materialism and empiricism. And then we look at theory and observation in science, which hit like empiricism. What's the role of a theory and observation in science? A topic we went more into detail. So that was my first foray into it, just a 4-hour video, and maybe that actually got the most views of any of them, because it's the first one. And the second one, they started getting a little bit longer. The second one, I reviewed part one. A lot of these I did review. And I talked about the scientific revolution, which there might be multiple scientific revolutions, like obviously Thomas Kuhn and the structure of scientific revolutions, but most notably the scientific revolution referring to Galileo, Descartes, and Newton. And then John Locke, the philosophy of science. John Locke is one of the main precursors, earlier founding members to the Royal Society and the philosophy that leads to empiricism, which becomes important for the philosophy of science. And within these series, I've also talked a little bit about the multiple truth hypothesis and the relationship. Then I went into scientific representation, which is a little bit about model theory and the certain how do you represent a scientific theory, how do you have a scientific model, like talked about like the different theories of pragmatism, or is a scientific theory only a scientific theory if it could be set up as a series of differential equations, or can you have a scientific theory that's explained in words, or the pragmatic approach, and generally like America philosophy is pragmatism. And then I went more in depth into the scientific method. We talked a lot about pragmatism and Charles Sanders Peirce, which just came up again and again. And I also talked a little bit about the philosophy of technology, a subject I like to return to. I was going to cover today the philosophy of architecture, but architecture is very loosely connected to the philosophy of science. So maybe I'll look at that on the week in review at some point. But technology is directly really what's the relationship between technology and science, and to some extent, technology predates the philosophy of science, because before there was science, there was technology. And how do you understand technology? And then even today, it's still unclear the connection. And we looked at Kant's philosophy of science, which Kant has been an extremely important player all across the philosophy of science and truth theory in general, and Western philosophy. So we've talked quite a bit about Kant. So in the third part, a little ramble, like why I'm doing this, metaphysics, philosophy of science, and talked about causality, going back to Kant and Hume. What is causality? What's the connection between causality and the scientific revolution? Reiner, I had this yarmulke before MAGA, so this is an old yarmulke. I don't wear that often, but it was before MAGA. It's old. So, but yeah, it might be the same color. It's like like the cardinal red, blood red, cardinal red. That might have some representation also. But the yarmulke predates MAGA. It's not a specific MAGA, but it might be the same blood red color. Okay, so we talked about Kant and Hume on causality. Very important. Precursors to philosophy, and something that week in review I really did a lot of in-depth analysis on Kant, and quite a bit on Hume, but mostly on Kant. Then we talked about the structure of scientific theories, the syntactic, semantic, and pragmatic views. What is a scientific theory, and how is it properly structured? Is it syntax, which would be logical formation, or semantic, which is in sentence, or more pragmatic, where just what works in scientific theories is a combination of multiple things put together that whatever works. That could include logical formulations, differential equations, and regular language sentences. And then we talked about neo-Kantianism with the Marburg School and the Southwest School, and Ernst Cassirer and Cohn were very important. On Week in Review, I talked about the Cassirer-Heidegger debate in Davos in 1929, which Rabbi Soloveitchik was at, related to truth theory. And then we went into the Vienna Circle, and so the philosophy of science 3 was very important, like the history of it, and leading up to the philosophy of science really starts with the Vienna Circle. So the precursors of Kant and Hume and neo-Kantianism, Hobbes, Newton, Descartes, you still have kind of the Cartesian viewpoint where you have the root being metaphysics, the branch being science, mathematics, and the branches being the fields of science. And it's not until the Vienna Circle that the philosophy of science, where science is stripped of its philosophical metaphysical precursors, and Kant lays the groundwork for the completion of Cartesian Newtonian science with metaphysical, even dualistic precursors for material understanding. And then the neo-Kantians advance on that, where they're not strict Kantians, and you look towards a moving forward where science is a process that moves people forward in a direction of discovery and understanding, and hopefully towards potentially a complete understanding, to the Vienna Circle, where to some extent the philosophy of science itself is stripped of the philosophical precursors. So in the fourth in the series, we looked at Hilbert's program, a topic that I've mentioned many, many times, and Hilbert's attempt, Hilbert as a student of the Vienna Circle at Göttingen, also something I covered in Week in Review in depth, is the goal to axiomatize science, unify science. So, the attempt to unify all knowledge in a scientific process, starting with the 23 questions that many of them are related to the unification of various fields of mathematics, logic, and science, and the attempt to create a universal system that could derive from that all knowledge, which largely failed with Gödel's incompleteness theorem. But so we talked about Hilbert's program, then the unity of science, the concept of the attempt to unify science, which was one of the main projects of the Vienna Circle, although there were attempts and other precursors to unify science, but that was one of the main concepts of the Vienna Circle. And then talked about Einstein's philosophy of science, where Einstein was largely a pragmatist and a picker and chooser. So Einstein's general method was to pick and choose. And Einstein, neo-Kantianism, logical empiricism, the Vienna Circle, Einstein talked and had communications with all sorts of people and had some conceptual basis for what we might call a philosophy of science, but Einstein did not necessarily have a consistent philosophy of science, and is more, symbolic of the post-Vienna Circle foray into America, where the combination of logical empiricism and pragmatism that we've been talking about recently on the Week in Review, and I'll probably continue to talk about on Week in Review at least this week. And then from there we talked about logical empiricism, which is, so there's logical positivism, and sometimes positivism just means empiricism. But sometimes they'll be classified as different schools between logical empiricism and logical positivism, although sometimes they're understood to be one and the same. But generally, logical empiricism, logical positivism, that's the mainstream school of the Vienna Circle that becomes dominant in the creation of the philosophy of science till today. So, what I'd done in the first 4 episodes was the philosophical precursor, some important ideas, but philosophy of science really ripens in between World War I and World War II with the Vienna Circle and the creation of logical positivism, and then coming to America after the war, even before World War II, logical positivism um, becomes less philosophical and more practical. So today, logical positivism is scientific. I talk about scientific realism later. We'll get to that, but it's like a precursor for scientific realism, and becomes the dominant school within science. Okay, so episode 5, and so these I did almost 1 week after the other. So like the first 5 episodes I did, basically 1 week after the other, covered a whole bunch, and then I took a hiatus till a few months ago, and now completing the series. So episode 5, I go over the various university programs, the few places, mostly derivatives of the Vienna Circle, that actually have degrees in philosophy of science and what makes up a degree in the philosophy of science. Then we talk about rationalism versus empiricism, the connection or uh, problems of rationalism and empiricism, and get more Kant and then scientific progress. What is scientific progress? We talk like inevitabilism, theory change. What does it mean to advance in science? What does it mean, to make progress in science? Is there even such a thing as progress in science? And then we talk about Karl Popper, falsibility, the various things. And I read most through, Karl Popper, including some of his thoughts on history, and the open society, like George Soros, but a lot of his school, and Popper, also a derivative of the Vienna Circle, next to Thomas Kuhn, one of the big names, also in the philosophy of science, the London School of Economics. And then we get to scientific realism, where scientific realism is the dominant paradigm today, where scientific realism is somewhat this derivative of the Vienna Circle of logical positivism with pragmatism, where conceptually saying that science realistically describes nature. They say, well, what is science? What is science exactly? Is it some from Kant and Descartes? You had somewhat a dualistic understanding that science. Where did science exist? Were they structures in the mind, Platonic forms, or is science a social construct? To the main school today of scientific realism, which is generally accepting the epistemic and metaphysical framework that science accurately represents reality. And from there, we looked at physicalism and materialism. And we'll talk a little bit more about that today with the mind-brain identity theorem. But connected with scientific realism, physicalism becomes the dominant approach, at least the majoritarian approach today, where most scientists are physicalists, at least most scientists in the West. And then from there, that was April 2nd last year. But from there, it wasn't until December, till 2 months ago. So it was like a full 7-8 months of break before I was able to continue the series, got caught up with other things. And although over that period, I probably read like 50 books. And maybe since I've started this, I've read like 100 books on the subject. So it's like a deep subject. And I was underprepared for how much precursor work was required to really give a good coverage of this topic. So over the last year, I've read close to 100 books. Week in review, I probably read 50 articles and various things. So finally got back to it at the beginning of December and continued the series. And We talked about the indispensable arguments for the philosophy of mathematics, where mathematics is indispensable to the philosophy of science. And because mathematics is indispensable to the philosophy of science, it becomes a necessary precursor. And even to say, well, what is mathematics? Because mathematics is necessary for science, it has some special status or elevate it to some sort of true level of assertion. Um, Sometimes also you could talk about logic, mathematics, and logic, sometimes meant to include each other, which gets back to the Hilbert program that you were talked about in episode 3 or 4. And they talk about scientific reduction, like reductionism. What does it mean to be able to reduce one idea to the other? What does it mean, like if one idea is more grounded, say that one could be derived from the other? The nature of causation, which when we next come to metaphysics, causation is largely one of the subjects of metaphysics that science needs. You need a metaphysical precursor framework to advance in science. But reductionism is an important topic, and can one theory be reduced to the other, or can biology be reduced to chemistry, which could be reduced to physics, or even within physics, could one theory be reduced to more base important theories, so on and so on. And then talk about the philosophy of neuroscience, very important. You write the biology, mechanisms, and consciousness, and then reductionism in biology, where you reduction in general, but the attempt to reduce biology to chemistry to physics. And then if that can't be done, what does that imply for the philosophy of biology? And in episode 7, talked about models in science. Um, what is a model? The tens, we talked about tens of different kinds of models: probing models, phenomenological models, computational models, developmental models, explanatory models, impoverished models, testing models, idealized models. And what does it mean to be a model? What does it mean to have different types of models? And specifically, what does it mean to be a scientific model? Are all models equal, or are some models more important than other types? Can you reduce some types of models to others, like mathematical models, logical representation models? And then we talked about realism and theory change. So we said scientific realism is the main school where most people believe that science accurately, realistically represents reality. Then what does it mean that theories change? If science is an accurate representation of reality and theories change over time, what does that tell us about? Does that mean that previous theories didn't accurately represent reality and the newer theory does, or that it partially represents reality? So, important topic. Then we talked about theoretical terms in science that like a mass and length and the very we various concepts. What does it mean, the theoretical terms? And then like Feyerabend and Kuhn, we talk about theory latedness, or the Quine-Duhem hypothesis, where science is theory laden because scientific theories are based on the theoretical terms, and the theoretical terms are somewhat self-descriptive and make science circular. So, importance, what does it mean, the theoretical terms in science? They're talked about ceteris paribus laws, which is Latin for all things being equal, or meaning like non-universal laws, rules, laws that have exceptions. In modern science, where historically like Newtonian mechanics and Galileo, uh, Descartes, Newton, where you wanted to have universal scientific theories, and up through the unification in the late 1800s of Kant, before biology and chemistry had become important sciences, where the attempt was in physics to have universal laws. But as biology and chemistry advanced, and even quantum physics, quantum mechanics, a deeper understanding of physics, it became clear that there's very few to no universal laws. All laws have exceptions, and specifically in biology, um, most laws only work under certain conditions. So you could have like a mechanism or something that happens under normal conditions, but conditions aren't always normal. So what does it mean to have non-universal scientific laws that only work under normal conditions? And if it doesn't work under abnormal conditions, what does that tell us about the law? And so there's a long past and a little bit related to economics also, where the main use of the ceteris paribus is in economics, because most cases in economics they're not universal and they are under normal conditions. So under non-normal, but also uh, most biological laws and chemistry laws and even a lot of physical laws fall under this non-universal ceteris paribus under normal conditions. And then we talked about mechanisms in science, where as opposed to the old school theories of physics that were usually formulated in terms of differential equations, where almost all of the new discoveries in science are in the field of biology, and biological theories of science are usually what they call mechanisms, biological mechanisms. Even sometimes in physics and astronomy and chemistry or material sciences, you say, well, it's not a universal law. We're not having like a new, like, Newton F equals ma. What you have is a mechanism. Like amino acids, or like viruses, the cleavage site from something like that, which is an is a mechanism the same thing as the law. So deep dive into mechanisms. And episode 8 last year. So we talked about scientific explanation, which is another way around. It's kind of like the Vienna Circle and scientific realism. What does science explain? So if you're not scientific realist, if science isn't a realistic explanation of reality, what is it? And so there's different schools, and a lot of this is more Vienna Circle and the students of the Vienna Circle, and different theories like the deductive nomenological model of the difference between a theory and a model. Then we looked at mathematical explanation, and in terms of mathematics, what is what does it mean? The connection between mathematics and science. We talked about the indispensability argument, but assuming that mathematics isn't indispensable, what does it mean to have a mathematical explanation in science, as opposed to like a causal mechanism? Is a causal and a mathematical explanation one and the same, or are they different? And what is more powerful in terms of science? Is the causal theory more important than the mathematical representation, or the other way around? So very important topic. Then we talked about scientific objectivity. Your question, is science objective, or is science a social construct? And here you have a lot of Feyerabend, and Feyerabend was a critic of science and talked about the subjectivity, or science as a social construct. And then we talked about incommensurability, a topic that is one of the major things in Thomas Kuhn's The Structure of Scientific Revolutions, where incommensurability means unmeasurable, means that the measure of one theory can't be compared to that of a different theory. So to say, does mass in physics mean the same thing as mass in chemistry, or the theoretical terms from one subfield of science to the other subfield of one theory? And it's related to like theory relatedness, where theories are self-referential, and what theoretical terms, classical concepts, or various things mean in one theory do not necessarily mean the same thing when applied to another theory. So an important concept, and a lot of these are hitting back on each other, one another, like reductionism. Can you reduce biology to chemistry to physics? And then we'll maybe the theoretical terms don't mean the same things. And then the last one, we talked about computer simulations in science. These days in modern science, almost everything, all theories are tested through computer simulations, the different types of computer simulations and Monte Carlo simulations, some relation to the multiple truth hypothesis, and the connection between science and computer simulation. The old school empiricism. What does it mean if things are measured by the computer, or derivative from a computer simulation, a computer program, as opposed to classical I observe handmade calculations. We talked about experiment in physics, as opposed to computer simulations. Can a computer simulation be considered an experiment? And the epistemology of experiment, the different types of experiment, and the implications. And then we talked about operationalism, where operationalism mostly, Piercy Bridgman, and like a theory of meaning, what we mean by a concept or an operation in science. What does it mean to have an operation? And some overlaid things like incommensurability, like the question of length, where if you define length by an operation, length means something different at the human level to the microscopic to the macroscopic level. It's measured differently, where I could measure length for construction using a ruler, but at the macroscopic level, it's done through instruments, and at the microscopic and macroscopic level, it's done through instruments and done through different instruments, and we call that an operation. And if it's not the same operation, does that mean that length is different? And you could use the same physics equations for length or even meters, but if the measurement of the operation is different at different scales and various topics, so important concept. And then I finally got to some of the deeper aspects in quantum mechanics. So a lot of people, like philosophy of science, most people, if they think about the philosophy of science, they haven't applied it to basic aspects like Newtonian or everyday science that maybe people understand. They're thinking in relation to like Einstein and quantum mechanics and the nature of reality. And so we got to the Copenhagen interpretation of quantum mechanics, and we talked about the different view between Bohr and Heisenberg and some of the other schools, and mathematical formulations, and how you understand things like classical terms and classical concepts within quantum mechanics. So the Schrodinger wave equation, the collapse of the wave equation, what do these things mean? And then finally looked at quantum theory and mathematical rigor, where one of the main precepts of quantum theory is the mathematical structure. Like we were talking about operationalism, where you can't measure with your eye, you need high level equipment, and the type of mathematical system you use is the difference between different ways of understanding quantum theory. And the question, we talked about indispensability or mathematics, mathematical representation in science, but at the quantum level, where quantum theories are completely dependent upon mathematical structures, and like rigged Hilbert space and Lagrangian, and the various factors. So a lot of that was quite complicated, and topic will return to, but the last one was the deepest I covered in relation to quantum theory and modern physics. So there you have it, and that gets us up to present, where now I will be covering 3 more issues today. Be reading today from 3 different papers. Maybe take me 2.5 hours, and then I will give some concluding remarks, and then I'll discuss metaphysics, which will be my next series, possibly even next Wednesday. But we'll see. And so, anyone tuning in, appreciate you tuning in. Hope this was useful to people. as I said, like, large extent, the due diligence for myself to, start writing and to be accurate in my terminology. Like, just streaming or want to start writing, and there's a lot of precursor information, and even, like Duvid, I'm somewhat like a perfectionist, um, and I want to know the stuff. I want to be right. Like, I don't want to just ramble random things. So, publicly, I've done, week in review in this series, a lot of due diligence in, um, understanding the Western canon. To some extent, modern science is the most important part of the Western canon. I mean, there's other aspects to the Western canon, but the Western canon is probably most important because science comes out of it. So you think like, Galileo, Descartes, Newton, Kant, Hobbes, Locke, the Vienna Circle, all these parts of the Western canon, the Royal Society of London, is, from my understanding, most important because modern mathematics and science derived out of the Western canon. So just to do the due diligence, who are the people, what was the historical order, the advent of this stuff, what did they say, um, and what's the current state today. So you talk about metaphysics or interfaith, dualism, non-dualism, monism, a lot of other topics I'll be returning to that, you could really only intelligently speak about within the framework of the philosophy of science. And so, like, the reality, the topic I wanted to cover most was the hard problem of consciousness and the philosophy of mind and psychology. The question, where does psychology lie? What is psychology? Is psychology a science? Is psychology a philosophy? Is it esoteric? And the hard problem of consciousness. And so, from having a lot of discussions, Kevin McCarran, who I came across in the middle of this series, but others, uh, modern day debate, Amy Newman, T Jump, the various people who debate things like evolution that haven't really done a deep dive into metaphysics and the philosophy of science. And very rarely do you meet people that have really delved into the subject. So, I was, as the due diligence, and then it just became interesting to myself, whether I'll use it, whether I'll be able to have conversations, whether, kind of like the debate me bro, where, people aren't really interested in learning something, so they just use kind of, um, debate me bro, sophist type tactics, as opposed to really delving and trying to understand something. So Duvid did the due diligence. And then also, okay, like, Duvid only has a bachelor's degree, I don't even have a master's degree. I took some master's level courses in civil engineering and a few other things, but I only have a bachelor's degree. And so my credentials, I also went to rabbinic school, but, to publicly, do my credentials, I'm not just, God forbid, talking out of my ass. Saying that I've done the due diligence, I've read the literature, and I'm going to say something over that I'm going to properly understand the precursor knowledge. So, like when I spoke to Ashish Delela, it's like there's always another name and another theory. So, like, what about, Kant, and what about Nietzsche, and what about, Feyerabend or Heidegger or Husserl, and, the important names. There's always more. There's always people you haven't heard of, but like some precursor to say, well, I know the main ideas and the main theories. I've done the due diligence. So, you're not going to be like, well, what about Heidegger, and like who's Heidegger, um, or, what about, um, the correspondence theory of truth, or these various concepts, like, are you a logical positivist, or these various nomenclatures, conventions of the people who are technical experts in the field. So most people don't know about this, but the few people who do study it, there is a conventional nomenclature of how these ideas are defined and their history to it. So Duvid has done the due diligence. I've done it publicly. So, hopefully some people have gained from this also. And, kind of just like a book on tape for people who listen to that, or, people who don't have as much time because, like, Duvid spent, tens of hours preparing each one of these. So like each one of these episodes, like I probably spent more than 4 hours for each 1 hour that I've streamed in preparation. and reading books like more than that. I probably spent another 4 hours reading on the subject and your related topics. So a lot of work, a lot of effort just to get this right, to really understand this stuff. To talking week in review of that guy Zargons, where what do you want from me, God? What am I here for? And I want the truth. I want to know. I want to understand. And that's my main desire. I desire to be a good person. I desire to serve God properly. In order to do that, I need to know the truth. And therefore, I've done this due diligence, and I've publicly done it. As so to say, a service. And so let's jump right in, and we're going to be looking at three things today. We're going to look at the mind-brain identity theory, the philosophy of statistics, that one is semi-long, and computational philosophy. And it might even only be 2 hours, so not super long today, but let's start with the mind-brain identity theory. And then from there, we'll go into statistics and then computational philosophy, and that will wrap up my series. And from there, give some concluding remarks and a preview of the metaphysics theory. The mind-brain identity theory. The identity theory of mind holds that states and processes of the mind are identical to states and processes of the brain. Strictly speaking, it need not hold that the mind is identical to the brain. Idiomatically, we do use she has a good mind or she has a good brain interchangeably, but we would hardly say that her mind weighs 50 ounces. Here I take identifying mind and brain as being a matter of identifying processes and perhaps states of the mind and brain. Consider an experience of pain or of seeing something or of having a mental image. The identity theory of mind is to the effect that these experiences are just brain processes, not merely correlated with brain processes. Some philosophers hold that though experiences are brain processes, they nevertheless have fundamentally non-physical, psychical properties, sometimes called qualia. Here I shall take the identity theory as denying the existence of such irreducible non-physical properties. Some identity theorists give a behavioralistic analysis of mental states, such as beliefs and desires, but others, sometimes called central state materialists, say that mental states are actual brain states. Identity theorists often describe themselves as materialists, but physicalist may be a better word. That is, one might be a materialist about the mind, but nevertheless hold that there are entities referred to in physics that are not happily described as material. In taking the identity theory in its various forms as a species of physicalism, I shall say that this is an ontological, not translational physicalism. It would be absurd to try to translate sentences containing the word brain and the word sensation into sentences about electrons, protons, and so on. Nor can we translate sentences concerning the word tree. After all, tree is largely learned ostensibly and not even part of botanical classifications. If we were small enough, a dandelion might count as a tree. Nevertheless, a physicalist could say that trees are complicated physical mechanisms. The physicalist will deny strong emergence in the sense of some philosophers such as Samuel Alexander and possibly C.D. Broad. The latter remarked, 1937, that as far as was known at the time, the properties of common salt cannot be deduced from the properties of sodium in isolation or of chlorine in isolation. He put it too epistemologically. Chaos theory shows that even in a deterministic theory, physical consequences can outrun predictability. Of course, the physicalist will not deny the harmless sense of emergence, in which an apparatus is not just a jumble of its parts. Historical antecedents. The identity theory, as I understand it, goes back to U.T. Place and Herbert Fagel in the 1950s. Historically, philosophers and scientists, for example, Leucippus, Hobbes, Lemaitre, and de Holbach, as well as Kurt Volk, who, following Pierre-Jean Georges Cabinis, made the posteritist remark, perhaps not meant to be taken seriously, that the brain secretes thought as the liver secretes bile, have embraced materialism. However, here I shall date interest in the identity theory from the pioneering paper, Is Consciousness a Brain Process by U.T. Place, 1956, and Fagel, The Mental and the Physical, 1958. Nevertheless, mention should be made of suggestions by Rudolf Carnap, 1932, Reichenbach, 1938, and Mort Schlick, 1935, of the Vienna Circle. Reichenbach said that mental events can be identified by the corresponding stimuli and responses, much as the possibly unknown internal state of the photoelectric cell can be identified by the stimulus light falling on it and response electric current flowing from it. In both cases, the internal states can be physical states. However, Carnap did regard the identity as a linguistic recommendation rather than asserting a question of fact. See his Herbert Fagel on Physicalism in Schlipp, 1963. The psychologist E.G. Boring, 1933, may well have been the first to use the term identity theory. Place's very original and pioneering paper was written after discussions at the University of Adelaide with J.J.C. Smart and C.B. Martin. For recollections of Martin's contributions to the discussion, see Place, 1989, Low Claim Assertions, and Hale, 1989. Smart, at the time, argued for a behavioralist position in which mental events were elucidated purely in terms of hypothetical propositions about behavior, as well as first-person reports of experience, which Gilbert Ryle regarded as avowals. Avowals were thought of as mere pieces of behavior, as if saying that one had a pain was just doing a sophisticated sort of winces. Smart saw Ryle's theory as friendly to physicalism, though that was not part of Ryle's motivation. Smart hoped that the hypotheticals would ultimately be explained by neuroscience and cybernetics, being unable to refute Place and recognizing the unsatisfactoriness of Ryle's treatment of inner experience, to some extent recognized by Ryle himself. Smart soon became converted to Ryle's view. In this, he was encouraged and influenced by Fagel's The Mental and the Physical. Fagel's wide-ranging contribution covered many problems, including those connected with intentionality, and he introduced the term nomological danglers for the dualist supposed mental-physical correlations. They would dangle from the nomological net of physical science and should strike one as implausible excrescences on the fair face of science. The nature of identity theory. Place spoke of constitution rather than of identity. One of his examples is this table is an old packing case. Another is lightning is an electric charge. Indeed, this latter was foreshadowed by Place in his early paper, The Concept of Heed, 1954, in which he took issue with Ryle's behavioralism as it applies to the concept of consciousness, sensation, and imagery. Place remarked the logical objections which might be raised to the statement consciousness is a process in the brain are no greater than the logical objections which might be raised to the statement lightning is a motion of electric charges. It should be noticed that Place was using the word logical in the way that it was used at Oxford at the time, not in the way that is normally used now. One objection was the sensation does not mean the same as brain process. Fagel and Smart put the matter more in terms of the distinction between meaning and reference. Sensation and brain process may differ in meaning and yet have the same reference. There did not seem to be a tendency among philosophers to have thought that identity statements needed to be necessary and a priori truths. However, identity theorists have treated sensations and our brain processes as contingent. We had to find out that the identity holds. Aristotle, after all, thought that the brain was for cooling the blood. Descartes thought that consciousness is immaterial. It was sometimes objected that the sensation statements are incorrigible, whereas statements about brains are corrigible. The inference was made that there may be something different about sensations. Ryle and in effect Wittgenstein toyed with the attractive but quite implausible notion that ostensible reports of immediate experience are not really reports but are avowals, as if my report that I have a toothache is just a sophisticated sort of wince. Place, influenced by Martin, was able to explain the relative incorrigibility of sensation statement by their low claims. I see a bent oar makes a bigger claim than it looks to me as if there is a bent oar. Nevertheless, my sensation and my putative awareness of the sensation are distinct existences, and so by Hume's principle, it must be possible for one to occur without the other. One should deny anything other than a relative incorrigibility. As remarked above, Place preferred to express the theory by the notion of constitution, whereas Smart preferred to make a prominent the notion of identity as it occurs in the axioms of identity and logic. So Smart had to say that if sensation X is identical to brain process Y, then if Y is between my ears and is straight or circular, absurdly to oversimplify, then the sensation X is in between my ears and is straight or circular. Of course, it is not presented to us as such in the experience. Perhaps only the neuroscientist could know that it is straight or circular. Phenomenal properties and topic neutral analysis. The question might be asked that even if sensations are identical with brain processes and are they not introspected, non-physical properties of sensations that are not identical with properties of brain processes? How would a physicalist identity theorist deal with this? The answer is that the properties of experience are topic neutral. Smart adapted the words topic neutral from Ryle, who used them to characterize words such as if, or, and, not, because. If you overheard only these words in conversation, you would not be able to tell whether the conversation was one of mathematics, physics, geology, history, theology, or many other subjects. Smart used the word topic neutral in the narrow sense of being neutral between physicalism and dualism. For example, going on, occurring, intermittent, waxing, waning are topic neutral. So is me, insofar as it refers to the utterer of the sentence in question. Thus, to say that a sensation before my eyes leaves it open as to whether the sensation is non-physical as the dualist believes or as physical as the materialist believes. The sentence also is neutral as to whether the properties of the sensation are physical or whether some of them are irreducibly physical. It is important for identity theorists to say that sense data and images are not part of the furniture of the world. This move should not be seen merely as ad hoc advice, since Ryle and Austin, in effect Wittgenstein, and others had provided arguments, as when Ryle argued that mental images were not a sort of ghostly picture postcard. Place characterized the fallacy of thinking that when we perceive something green, we are perceiving something green in the mind as the phenomenological fallacy. He characterized this fallacy. Eliezer, is my old friend from Renaissance Catering in Bubba. If it's you, Baruch Hashem, good to hear from you. Been a long time. Talking now about philosophy of science. And in fact, we used to talk about this also. If you used to come to my apartment in Borough Park, that was my favorite topic then, as it is now. He characterized this fallacy, the mistake of supposing that when the subject describes his experience, when he describes how things look, sound, smell, taste, or feel to him, he is describing the literal properties of objects and events on a peculiar sort of internal cinema or television screen, usually referred in the modern psychological literature as the phenomenal field. So I want to keep on topic. My phone number is the same. I heard you moved to Jerusalem, like opened up a bar or whatever. I think I'm still friends with your brother on Facebook, but you'll feel free to contact me. Or you'll leave a message with your contact. I'll look back. I'm going to be reading this for about 2 hours, but great to see you. Of course, as Smart recognized, this leaves the identity theory dependent on a physicalist account of color. His early account of color, 1961, was too behavioralist and could not deal, for example, with the reversed spectrum problem, but he later gave a realist and objectivist account. Armstrong had been realist about color, but Smart worried that if so, color would be very idiosyncratic and disjunctive concept of no cosmic importance, of no interest to extraterrestrials, for instance, who had different visual systems. Prompted by Lewis in conversation, Smart came to realize that this was no objection to colors being objective properties. One first gives the notion of normal human percipient with respect to color, for which there are objective tests in terms of ability to make discriminants with respect to color. This can be done without circularity. Thus, discriminate with respect to color is more primitive notion than is that of color. Compare the way that is set theory equinumerous is antecedent to number. Then Smart elucidated the notion of color in terms of the discriminations with respect to color of normal human percipients in normal conditions. This account of color may be disjunctive and idiosyncratic. Anthropocentric and disjunctive they may be, but objective nonetheless. David R. Hilbert, 1987, identifies colors with reflectances, thus reducing the idiosyncrasy and disjunctiveness. A few epicycles are easily added to deal with radiated light, the colors of rainbows or the sun at sunset, and the colors due to diffraction from feathers. John Locke was on the right track in making the secondary qualities objective as powers in the object, but erred in making these powers to be powers to produce ideas in the mind rather than to make behavioral discriminations. Also, Smart would say that if powers are dispositions, we should treat the secondary qualities as the categorical basis of these powers. In the case of colors, properties of the surfaces of objects. Locke's view suggested that the ideas have mysterious quality observed on the screen of the internal mental theater. However, to do Locke justice, he does not talk in effect of red ideas, but of ideas of red. Philosophers who elucidate in is red in terms of looks red have the matter the wrong way around. The identity theorist can say that sense data and images are not real things. In the world, they are like the average plumber. Sentences ostensibly about the average plumber can be translated into or elucidated in terms of sentences about plumbers. So also there is having a green sense datum or image, but not sense data or images. And the having a green sense datum or image is not itself green. So it can, as far as this goes, easily be a brain process which is not green either. Thus, place when we describe the after image as green, we are saying that we are having the sort of experience which we normally have when, and which we have learned to describe as looking at a green patch of light. And Smart 1959 says, when a person says, I see a yellowish orange after image, he is saying something like there is something going on, which is like what is going on when I have my eyes open, am awake, and there is an orange illuminated in good light in front of me. Quoting these passages, David Chalmers, 1996, objects that if something is going on, is construed broadly enough to be inadequate, and if it is construed narrowly enough to cover only experiential states or processes, it is not sufficient for the conclusion. Smart would counter this by stressing the word typically. Of course, a lot of things go on in me. However, they do not typically go on then. They go on at other times too. Against place, Chalmers says the word experience is unanalyzed, and so place analysis is insufficient towards establishing an identity between sensations and brain processes. As against Smart, he says that leaving the word experience out of the analysis renders it inadequate. That is, he does not accept the topic neutral analysis. Smart hopes and Chalmers denies that the account in terms of typically of saves the topic neutral analysis. In defense of place, one might perhaps say that it is not clear that the word experience cannot be given a topic neutral analysis, perhaps building on Farrell, 1950. If we do not need the word experience, neither do we need the word mental. Rosenthal, 1994, complains against the identity theorist that experiences have some characteristically mental properties and that we inevitably lose the distinctively mental if we construe these properties as neither physical nor mental. Of course, to be topic neutral is to be able to be both physical and mental, just as arithmetic is. There is no need for the word mental itself to occur in the topic neutral formula. Mental, as Ryle suggests, is in its ordinary use is rather grab bag term, mental arithmetic, mental illness, with which an identity theorist finds no trouble. Just curious if I'm glad to see my old friend Laser Cone, and just check he's got a channel. So hopefully we'll reach out and we'll talk a different time. Okay, causal role theories. In their accounts of mind, David Lewis and Armstrong emphasized the notion of causality. Lewis's 1966 was a particularly clear-headed presentation of identity theory in which he says, my argument is this: the definitive characteristic of any sort of experience as such is its causal role, its syndrome of most typical causes and effects. But we materialists believe that these causal roles, which belong by analytic necessity to experiences, belong in fact to certain physical states. Since these physical states possess the definitive character of experiences, they must be experiences. Similarly, Robert Kirk, 1999, has argued for the impossibility of zombies. It is if the supposed zombies had all the behavioral and neural properties ascribed to it by those who argue from the possibility of zombies against materialism, then the zombie is conscious and so not a zombie. Thus, there's no need for the explicit use of Occam's razor as in Smart 1959, though not in Place 1956. Lewis's paper was extremely valuable, and already there are hints of the marriage between the identity theory of mind and the so-called functionalist ideas that are explicit in Lewis' 1972 and 94. In his 1972 psychophysical and theoretical identifications, he applies ideas in his more formal paper, How to Define Theoretical Terms, 1970. Folk psychology contains words such as sensation, perceive, believe, desire, emotion, etc., which we recognize as psychological. Words for color, smell, sounds, taste, and so on are also occur. One can regard common sense platitudes containing both these sorts of these words as constituting a theory, and we can take them as theoretical terms of common sense psychology, and thus as denoting whatever entities or sorts of entities uniquely realize the theory. Then, if certain neural states do not do so too, as we believe, then the mental states must be these neural states. In his 1994, he allows for the tact in extracting a consistent theory from common sense. One cannot uncritically collect platitudes, just as in producing a grammar implicit in our speech patterns, one must allow for departures from what on our best theory would constitute grammatically. A great advantage of this approach over the early identity theory is its holism. Two features of this holism should be noted. One is that the approach is able to allow for the causal interactions between brain states and processes themselves, as well as in the case of external stimuli and responses. Another is the ability to draw on the notion of ramification of theory. F.P. Ramsey had shown how to replace the theoretical terms of a theory, such as the property of being an electron, by the property X, so that when this is done for all the theoretical terms, we are left only with a property X such that, property Y such that. Take the terms describing behavior as an observation terms and psychological terms as the theoretical ones of folk psychology. Then ramification shows that folk psychology is compatible with materialism. This seems right, though perhaps the earlier identity theory deals more directly with reports of immediate experience. The causal approach was also characteristics of D.M. Armstrong's careful conceptual analysis of mental states and processes such as perception and the secondary qualities, sensation, consciousness, beliefs, desires, emotions, voluntary actions, in his A Materialist Theory of the Mind, 1968, with a second edition, 1993, containing a valuable new preface. Parts 1 and 2 of the book are concerned with the conceptual analysis, paving the way for contingent identification of mental states and processes with material ones. As had Brian Medlin in an impressive critique of Ryle and defense of materialism, Armstrong preferred to describe the identity theory as central state materialism, independently of Armstrong and Lewis. Medlin's central state materialism depended, as theirs did, on a causal analysis of concepts of mental states and processes. Mention should particularly be made here of two of Armstrong's other books, one on perception, 1961, and one on bodily sensations, 1962. Armstrong thought that of perception as coming to believe by means of the senses. This combines the advantages of direct realism with hospitality towards the scientific causal story, which had been thought to have supported the earlier representative theory of perception. Armstrong regarded bodily sensations as perceptions of states of our body. Of course, the latter may be mixed up with emotional states, as an itch may include a propensity to scratch, and contrariwise, in exceptional circumstances, pain may be felt without distress. However, Armstrong sees the central notion here as that of perception. This suggests a terminological problem. Smart had talked of visual sensations. These were not perceptions, but something which occurred in perception. So in this sense of sensation, there should be a bodily sensations. The ambiguity could perhaps be resolved by using the word sensing in the context of visual, auditory, tactile, and bodily, so that bodily sensations would be perceivings which involved introspectable sensings. These bodily sensations are perceptions, and there can be misperceptions, as when a person with his foot amputated can think that he has a pain in the foot. He has a sensing having pain in the foot, but the world does not contain a pain in the foot, just as it does not contain sense data or images, but does contain having the sense data and of images. Armstrong's central state materialism involved identifying beliefs and desires with the states of the brain. Smart came to agree with this. On the other hand, Place resisted the proposal to extend the identity theory to dispositional states such as beliefs and desires. He stressed that we do not have privileged access to our beliefs and desires like Ryle. He thought of beliefs and desires to be elucidated by means of hypothetical statements about the behavior and gave the analogy of the horsepower of a car. However, he held that the dispute here is not so much about the neural basis of mental states as about the nature of dispositions. His views on dispositions are argued at length in his debate with Armstrong and Martin. Perhaps we can be relaxed about whether mental states such as beliefs and desires are dispositions or a topic neutrally described neurophysiological states and return to what seems to be more difficult issue of consciousness. Causal identity theories are closely related to functionalism, to be discussed in the next section. Smart had been wary of the notion of causality in metaphysics, believing that it had no place in theoretical physics. However, even so, he should have admitted it in folk psychology and also in scientific psychology and biology generally, in which physics and chemistry are applied to explain generalizations rather than strict laws. In folk psychology, uses the if folk psychology uses the notion of causality, it is no matter if it is what Quine has called second grade discourse involving the very contextual notions of modality. Functionalism and identity theory. It has commonly been thought that the identity theory has been superseded by a theory called functionalism. It could be argued that functionalists greatly exaggerate their differences from identity theorists. Indeed, some philosophers such as Lewis and Jackson, Prageter and Pryor have seen functionalism as a route towards an identity theory. Like Lewis and Armstrong, functionalists define mental states and processes in terms of their causal relations to behavior, but stop short of identifying them with their neural realizations. Of course, the term functionalism has been used vaguely and in different ways, and it could be argued that even the theories of Place, Smart, and Armstrong were at bottom functionalists. The word functionalist has affinities with that of function in mathematics and also with that of function in biology. In mathematics, a function is a set of ordered n tuples. Similarly, if mental processes are defined directly or indirectly by sets of stimulus-response pairs, the definitions could be seen as functional in the mathematical sense. However, there is probably be a closer connection with the term as used in biology, as one might define eye by its function, even though a fly's eye and a dog's eye are anatomically and physiologically very different. Functionalism identifies mental states and processes by means of their causal roles, and as noted above in connection with Lewis, we know that the functional roles are possessed by neural states and processes. There are teleological and homuncular forms of functionalism, which are not considered here. Nevertheless, an interactionalist dualist, such as the eminent neurophysiologist Sir John Eccles, would implausibly for most of us all deny that all functional roles are so possessed. One might think of folk psychology, indeed much of cognitive science too, as analogous to block diagram in electronics. A block in the diagram might be labeled intermediate frequency amplifier while remaining neutral as to the exact circuit and whether the amplification is carried out by a thermionic valve or by a transistor. Using terminology of Jackson and Petit, the roll state would be given by an amplifier. The realizer state would be given by a thermionic valve, say. So we can think of functionalism as a black box theory. This line of thought would be pursued in the next section. Thinking very much of causal terms about belief and desires fits it in very well, not only with folk psychology, but also with Humean ideas about the motives of action. Though this point of view has been criticized by some philosophers, it does seem to be right. The existence of propulsive mechanisms has at last, I hope, shown to philosophers that there is nothing mysterious about teleology, nor are there any great semantic problems over intentionality. Consider the sentence generally, Joey believes true S, or Joe desires true S, where S is an appropriate sentence. One, of course, if one does not want to relativize to a language, one needs to insert or some same sayer of S or use the word proposition, and this involves the notion of proposition or intranslatability. Even if one does not accept Quine's notion of indeterminacy of translation, there's still fuzziness in the notion of belief and desire arising from the fuzziness or analyticity and synonymy. The identity theorists could say that on any occasion this fuzziness is matched by the fuzziness of the brain state that constitutes the belief or desire. Just how many interconnections are involved in a belief or desire? On a holistic account such as Lewis's, one need not suppose that individuation of beliefs and desires is precise, even though good enough for folk psychology and human mathematics. Thus, the way in which the brain represents the world might not be like a language. The representation might be like a map. A map relates every feature on it to every other feature. Nevertheless, a map contains a finite amount of information. They have not indefinitely many parts, still less continuum many. We can think of beliefs as expressing the different bits of information that could be extracted from the map. Thinking in this way, beliefs would correspond near enough to the individualist beliefs characteristic of folk and human psychology. Type and token identity theories. The notion of type and token here comes from an analogy from type and token as applied to words. A telegram love and love and love contains only 2 type words, but in another sense, as the telegram clerk would insist, it contains 5 words, token words. Similarly, a particular pain, more exactly a having a pain, according to the token identity theory, is identical to a particular brain process. A functionalist could agree to this. Functionalism came to be seen as an improvement on the identity theory and is inconsistent with it because of the correct assertion that a functional state can be realized by quite different brain states. Thus, a functional state might be realized by a silicon-based brain as well as by a carbon-based brain. As far as this goes, a functionalist can at any rate accept token identities. Functionalists commonly deny type identities. However, Jackson, Pargeter, and Pryor 1982, and Braddon, Mitchell, and Jackson 1996 argue that this is an overreaction on the part of the functionalists. Indeed, they see functionalism as a route to identity theory. The functionalists may define mental states as having some state or other which accounts for the functional properties. The functionalist second order state is the state of having some first order state or other which causes or is caused by the behavior to which the functionalist alludes. In this way, we have a second order type theory. This way of looking at matter is perhaps more plausible in relation to mental states such as beliefs and desires that it is to immediately reported experiences. If we continue to concern ourselves with first order properties, we could say that the type token distinction is not an all or nothing affair. We could say that human experiences are brain processes of one lot or sorts, and Alpha Centaurian experiences are brain processes of another lot or sorts. We could indeed propose much finer classifications without going to the limit of mere token identities. How restricted should the restriction of a restricted type theory? Even in the case of a similarity of my pain now to my pain 10 minutes ago, there will be unimportant dissimilarities and also between my pain and your pain. Whether we say that these two things are similar or not is a matter of abstractness of description. If we were to go to the limit of concreteness, the types would shrink to a single membered types, but there would be no ontological difference between identity theory and functionalism. An interesting form of token identity theory is the anomalous monism of Davidson, 1980. Davidson argues that causal relationships occur under the neural descriptions, but not under the descriptions of psychological language. The latter descriptions use intentional predicates, but because of indeterminacy of translation and of interpretation, these predicates do not occur in lost statements. It follows that mind-brain identities can occur only in the level of individual token events. It would be beyond the scope of the present essay to consider Davidson's ingenious approach, since it differs importantly from the more usual form of identity theory. Consciousness. Place answer the question, is consciousness a brain process? In the affirmative. But what sort of brain process? Is it natural to feel that there is something ineffable about which no mere neurophysiological process with only physical intrinsic properties could have? There is a challenge to the identity theorists to dispel this feeling. So let me use the word awareness for this automatic and subconscious sort of consciousness. Perhaps I am not 100% on automatic pilot. For one thing, I might be absent-minded in thinking about philosophy. One might indeed wonder whether one is ever 100% on automatic pilot, and perhaps one hopes that one isn't. Still, it probably does happen. Is perceiving in the sense of coming to believe by means of the senses. The driver gets the belief, but is not aware of doing so. There is no suggestion of ineffability in the sense of consciousness, for which I shall reserve the term awareness. For the full consciousness, the one that puzzles us and suggests ineffability, we need the sense elucidated by Armstrong in his debate with Norman Malcolm. Somewhat similar views have been expressed by other philosophers such as Savage, 1976, Dennett, 1991, Micon, 1996, and Rosenthal. A recent presentation of it is in Smart, 2004. In the debate with Norman Malcolm, Armstrong compared consciousness with proprioception. A case of proprioception occurs with our eyes shut and without touch. We are immediately aware of the angle at which one of our elbows is bent. That is, proprioception is a special case different from that of bodily sensation, in which we become aware of our body, of parts of our body. Now, the brain is part of our body, and so perhaps immediate awareness of the process in or a state of our brain may here for present purposes be called proprioception. Thus, the proprioception, even though the neuroanatomy is different, thus the proprioception which constitutes consciousness as distinguished from mere awareness is a higher order awareness, a perception of one part of or configuration in our brains by the brain itself. Some may sense circularity here. If so, let them suppose that the proprioception occurs in practice negligible time after the process propriocepted. Then perhaps there can be proprioceptions of proprioceptions, proprioceptions of proprioceptions of proprioceptions, and so on up, though in fact the sequence will probably not go up more than 2 or 3 steps. The last proprioception in the sequence will not be propriocepted, and this may help to explain our sense of the ineffability of consciousness. Compare Gilbert Ryle in The Concept of Mind on the systematic elusiveness of I. Places argued that the function of the automatic pilot, to which he refers as the zombie within, is to alert consciousness to inputs which it identifies as problematic, while it ignores non-problematic inputs or reroutes them to outputs without the need for conscious awareness. Later objections to the identity theory. Mention should here be made of the influential criticisms of the identity theory by Saul Kripke and David Chalmers, respectively. It will not be possible to discuss them in great detail, partly because of the fact that Kripke's remarks rely on views about modality, possible world, semantics, and essentialism, which some philosophers would want to contest, and because Chalmers' long and rich book would deserve a lengthy answer. Kripke, 1980, calls an expression a rigid designator if it refers to the same object in every possible world, or in a counterpart theory, it would have exactly similar counterparts in every possible world. It seems to me that what we count as counterparts is highly contextual. Kripke considers the identity heat equals molecular motion and holds that this is true in every possible world, and so is a necessary truth. Actually, the proposition is not quite true, for what about radiant heat? What about heat as defined in classical thermodynamics, which is topic neutral compared with statistical thermodynamics? Still suppose that heat has an essence and that it is molecular motion, or at least it is in the context envisaged. Kripke says that when we think that molecular motion might exist in the absence of heat, we are confusing this with thinking that the molecular motion might have existed without being felt as heat. He asks whether it is analogously possible that if pain is a certain sort of brain process, that it has existed without being felt as pain. He suggests that the answer is no. An identity theorist who accepted the account of consciousness as a higher order perception could answer yes. We might be aware of the damaged tooth and also of being in an agitation condition, to use Ryle's term for emotional states, without being aware of our awareness. An identity theorist such as Smart would prefer to talk of having pain rather than of pain. Pain is not part of the furniture of the world any more than sense datum about the average plumber is. Kripke concludes that the apparent contingency of the connection between the mental state and the corresponding brain state thus cannot be explained by some sort of qualitative analog, as in the case of heat. Smart would say that there is a sense in which the connection of sensation, sensing, and brain processes is only half contingent. A complete description of the brain state or process, including causes and effects of it, would imply the report of inner experience, but the latter, being topic neutral and so very abstract, would not imply the neurological description. Chalmers, 1996, in the course of his exhaustive study of consciousness, developed a theory of non-physical qualia, which to some extent avoids the worry about nomological danglers. The worry expressed by Smart in 1959 is that if there were non-physical qualia, there would most implausibly have to be laws relating neural physiological processes to apparently simple properties, and the correlation laws would have to be fundamental, mere danglers from the nomological sets, as Bagel called it, of science. Chalmers countered this by supposing that the qualia are not simple but unknown to us, are made up of simple proto-qualia, and that the fundamental laws relating to these physical entities relate them to fundamental physical entities. His view comes to a rather interesting panpsychism. On the other hand, if the topic neutral account is correct, then qualia are no more than points in a multidimensional similarity space, and the overwhelming plausibility will fall on the side of the identity theorist. On Chalmers' view, how are we aware of non-physical qualia? It has been suggested above that this inner awareness is proprioception of the brain by the brain. But what sort of story is possible in the case of awareness of a qualia? Chalmers could have some sort of answer to this by means of his principle of coherence, according to which the causal neurological story parallels the story of succession of qualia. It is not clear, however, that this would make us aware of the qualia. People often think that even if a robot could scan its own perceptual processes, this would not mean the robot was conscious. This appeals to our intuition, but perhaps we could reverse the argument to say that because the robot can be aware of its awareness, the robot is conscious. I've given reason above to distrust intuitions, but in any case, Chalmers comes some of the way in that he toys with the idea of a thermostat has a sort of protoqualia. The dispute between identity theorists and physicalists generally, and Chalmers comes down to our attitude to phenomenology. Certainly, walking in a forest, seeing the blue of the sky, the green of the trees, the red of the track, one may find it hard to believe that our qualia are merely points in a multidimensional similarity space, but perhaps this is what it is like, to use a phrase that it can be distrusted, to be aware of a point in multidimensional similarity space. One might also, as Place would suggest, to be subject to the phenomenological fallacy. As the end of his book, Chalmers makes some speculations about the interpretations of quantum mechanics. If they succeed, then perhaps we could envisage Chalmers' theory as integrated into physics and him as a physicalist after all. However, it could be doubted whether we need to go down to the quantum level to understand consciousness, or whether consciousness is relevant to quantum mechanics. Okay, so there you have important aspects, something that I'll return to again and again. One of the main reasons I did this series was to get deeper into the philosophy of mind, the hard problem of consciousness, and this question of the identity, mind-brain identity theory of physicalism. Does the mind derive from the brain, or Duvid as a dualist? What does it mean that Duvid is a dualist, and saying that the mind is independent of the brain? So Duvid is in direct opposition to the mind-brain identity theorem, but you have to do the due diligence. And I actually have an article from Place to read on Week in Review, so we'll go more in depth into this. So another important topic is statistics. So we discovered that we discussed the indispensability of mathematics and mathematical realism in science, and mathematics is clearly directly related to science, that most good scientific laws are purely described in mathematics. Mathematics is predictive, that science is predictive in a mathematical sense. But at a deeper level of the mathematics is statistics, that most things are not strictly determinative and only have statistical probability. So, and especially within consciousness, where you have Bayesianism, and then next we'll talk about computation, which is most important for consciousness and theories of mind. But almost all science these days, especially like quantum mechanics, is statistical in nature. So you can do the deep dive overview of the philosophy of statistics as an adjunct topic to the philosophy of science. Philosophy of statistics. Statistics investigates and develops specific methods for evaluating hypotheses in the light of empirical facts. A method is called statistical and thus the subject of study in statistics. If it relates facts and hypotheses of a particular kind, the empirical facts must be codified and structured into data sets, and the hypothesis must be formulated in terms of probability distribution over possible data sets. The philosophy of statistics concerns the foundations and the proper interpretation of statistical methods, their input, and their results. Since statistics is relied upon in almost all empirical scientific research, serving to support and communicate scientific findings in the philosophy of statistics is of key importance to the philosophy of science. It has an impact on the philosophical appraisal of scientific method and on the debate over the epistemic and ontological status of scientific theory. The philosophy of statistics harbors a large variety of topics and debates. Central to this is the problem of induction, which concerns the justification of inferences or procedures that extrapolate from data to predictions and general facts. Further debates concern the interpretation of the probabilities that are used in statistics and the wider theoretical framework that may ground and justify the correctness of statistical methods. A general introduction to these themes is given in section 1 through 4, provide an account of how these themes play out in two major theories of statistical method, classical and Bayesian statistics respectively. Section 5 directs attention to the notion of a statistical model, covering model selection and simplicity, but also discussing statistical techniques that do not rely on statistical models. Section 6 briefly mentions relations between the philosophy of statistics and several other themes from the philosophy of science, including confirmation theory, evidence, causality, measurement, and scientific methodology in general. And so note that the main parts I'm not reading are the examples and overly technical parts. So I'll be reading most of this besides the examples and the over technical parts. People could follow along and fill that in on their own. Statistics and induction. Statistics is a mathematical and conceptual discipline that focuses on the relation between data and hypothesis. The data are recordings of observations or events in a scientific study, a set of measurements of individuals from a population. The data actually obtained are variously called the sample data, or simply the data. And all possible samples from a study are collected in what is called sample space. The hypotheses, in turn, are general statements about the target system of the scientific study, expressing some general fact about all individuals in the population. A statistical hypothesis is a general statement that can be expressed by a probability distribution over sample space. It determines a probability for each of the possible samples. Statistical methods provide the mathematical and conceptual means to evaluate statistical hypotheses in light of a sample. To this end, the methods employ probability theory and, incidentally, generalizations thereof. The evaluations may determine how believable a hypothesis is, whether we may rely on the hypothesis in our directions, how strong the support is that the sample gives to the hypothesis, and so on. Good introductions to statistics abound. According to the so-called null hypothesis test, a decision is warranted if the data actually obtained are included in a particular region within sample space whose total probability does not exceed some specified limit, standardly set at 5%. The basic pattern of a statistical analysis is thus familiar from inductive inference. We input the data obtained thus far, and the statistical procedures output a verdict or evaluation that transcend the data, a statement that is not entailed by the data alone. If the data are indeed considered to be the only input, and if the statistical procedure is understood as an inference, then statistics is concerned with amplitude inference. Roughly speaking, we get out more than we have put in. And since the amplitude inference of statistics pertain to future or general state of affairs, they are inductive. However, the association of statistics with amplitude and inductive inference is contested, both because statistics is considered to be non-inferential by some and non-amplitude by others. Despite such disagreements, it is insightful to view statistics as a response to the problem of induction. The problem first discussed by Hume is treatise of human nature, but prefigured already by ancient skeptics like Sextus Empiricus, is that there is no proper justification for inferences that run from given experience to expectations about the future. Transposed to the context of statistics, it reads that there is no proper justification for procedures that take data as input and that return a verdict and evaluation or some other piece of advice that pertain to the future or to general states of affairs. Arguably, much of the philosophy of statistics is about coping with this challenge by providing a foundation of the procedures that statistics offers, or else by reinterpreting what statistics delivers so as to evade the challenge. It is debatable that philosophers of statistics are ultimately concerned with the delicate, even ethereal issue of justification of induction. In fact, many philosophers and scientists accept the fallibility of statistics and find it more important that statistical methods are understood and applied correctly. And is so often the case, the fundamental philosophical problems serve as a catalyst. The problem of induction guides our investigations into the workings, the correctness, and the conditions of applicability of statistical methods. The philosophy of statistics, understood as the general header under which these investigations are carried out, is thus not concerned with ephemeral issues, but represents a vital and concrete contribution to the philosophy of science and to science itself. Foundations and interpretations. While there is a larger variation in how statistical procedures and inferences are organized, they all agree on the use of modern measure theoretic probability theory, or a near kin, as the means to express hypotheses and relate them to data. By itself, a probability function is simply a particular kind of mathematical function used to express the measure of a set. The collection of sets generated by the operation of complement and join is called in algebra denoted S. Now, what does the probability function mean? The mathematical notion of probability does not provide an answer. The function P may be interpreted as physical, namely the frequency or propensity of the occurrence of a state of affairs, often referred to as chance, or else as epistemic, merely the degree of belief in the importance of the state of affairs, the willingness to act on its assumption, a degree of support or confirmation, or similar. This distinction should not be confused with that between objective and subjective probability. Both physical and epistemic probability can be given an objective and subjective character in the sense that both can be taken as independent or dependent of a knowing subject and his conceptual apparatus. In this context, the key point is that the interpretations can all be connected to foundational programs for statistical procedures. Although the match is not exact, the two major types specified above can be associated with the two major theories of statistics, classical and Bayesian statistics, respectively. Physical probability and classical statistics. In the sciences, the idea that probabilities express physical states of affairs, often called chances or stochastic processes, is most prominent. They are relative frequencies in a series of events, or alternatively, they are tendencies or propensities in the systems that realize those events. More precisely, the probability attached to the property of an event type can be understood as the frequency or tendency with which that property manifests in a series of events of that type. The mathematician Venn, 1988, and scientists like Quetelet and Maxwell are early proponents of this way of viewing probability. Philosophical theories of propensities were first coined by Peirce in 1910 and developed by Popper, 1959, Meller, 1971, Bigelow, 1977, and Geary, 1976. A rigorous theory of probability as frequency was first devised by von Mises, 1981, and also defended by Reichenbach, 1938, and beautifully expounded by van Lambergen, 1987. The notion of physical probability is connected to one of the major theories of statistical method, which has come to be called classical statistics. It was developed roughly in the first half of the 20th century, mostly by mathematicians and working scientists like Fisher, Wald, Nyman, and Pearson, and refined by very many classical statisticians in the last few decades. The key characteristics of the theory of statistics aligns naturally with viewing probabilities as physical chances, hence pertaining to observable and repeatable events. Physical probability cannot meaningfully be attributed to statistical hypotheses, since hypotheses do not have tendencies or frequencies with which they come about. They are categorically true or false once and for all. Attributing probability to hypothesis seems to entail that the probability is read epistemically. Classical statistics is often called frequentist, owing to the centrality of frequencies of events in classical procedures and the prominence of the frequentist interpretation of probability developed by von Mises. In this interpretation, chances are frequencies or proportions in a class of similar events or items. They are best thought of as analogous to other physical quantities like mass and energy. It deserves emphasis that frequencies are thus conceptually prior to chances. In propensity theory, the probability of an individual event or item is viewed as a tendency in nature, so that the frequencies or the proportion in a class of similar events or items manifest as a consequence of the law of large numbers. In the frequentist theory, by contrast, The proportions laid down indeed define what the chances are. This leads to a central problem for frequentist probability, the so-called reference class problem. It is not clear what class to associate with an individual event or item. One may argue that the class needs to be narrow as it can be, but in the extreme case of a singleton class of events, the chances, of course, trivialize to 0 or 1. Since classical statistics employs non-trivial probability that attach to a single case in its procedures, a fully frequentist understanding of statistics arguably is in need of a response to the reference class problem. Epistemic probability in statistical theory. There is an alternative way of viewing the probabilities that appear in statistical methods. They can be seen as expressions of epistemic attitudes. We are again facing several interrelated options. Very roughly speaking, epistemic probabilities can be stochastic, decision theoretic, or logical. Types of epistemic probability. Probabilities may be taken to represent stochastic attitudes in the sense that they specify opinions about data and hypotheses of an idealized rational agent. The probability then expresses the strength or degree of belief. They may also be taken as decision theoretic as part of a more elaborate representation of the agent, which determines dispositions towards decisions and actions about the data and the hypothesis. Oftentimes, a decision theoretical representation involves a stochastic attitude alongside preferential and perhaps other ones. Finally, the probabilities may be taken as logical. More precisely, a probabilistic model may be taken as logical, a formal representation that fixes a normative idea for uncertain reasoning. According to the latter opinion, probability values over data and hypotheses have a role that is comparable to the role of truth values in deductive logic. They serve to secure a notion of valid inference without carrying the suggestion that the numeric values refer to anything psychologically salient. The epistemic view of probability came into development in the 19th and the first half of the 20th century, first by the hands of De Morgan, 1847, and Boole, 1854, later by Keynes, 1921, Ramsey, 1926, and De Finetti, 1937, and by decision theorists, philosophers, and inductive logicians such as Carnap, 1950, Savage, 1962, Levy, 1980, and Jeffrey, 1992. Important proponents of these views in statistics were Jeffreys, 1961, Edward, 1972, Lindley, 1965, Good, 1983, and James, 2003, as well as very many Bayesian philosophers and statisticians of the last few decades. All of these have a view that places probabilities somewhat in the realm of epistemic rather than physical, not as part of a model of the world, but rather as a means to model a representing system like the human mind. The above division is certainly not complete, and it is blurry at the edges. For one, the stochastic notion of probability has mostly been spelled out in a behavioralist manner with the help of decision theory. Many have adopted so-called Dutch book arguments to make the degree of belief precise and to show that it is indeed captured by the mathematical theory of probability. According to such arguments, the degree of belief in the occurrence of an event is given by the price of a betting contract that pays out one monetary unit if the event manifests. However, there are alternatives to this behavioralist take on probability as stochastic attitude using accuracy or proximity to the truth. One of these are versions or extensions of the argument proposed by De Finetti, 1974. Others have developed an axiomatic approach based on natural desiderata for degrees of belief. Furthermore, as alluded to above, with the stochastic conception of probability, we can make a further subdivision into subjective and objective stochastic attitudes. The defining characteristics of an objective stochastic probability is that it is constrained by the demand that the beliefs are calibrated to some object fact or state of affairs, or else by further rationality criteria. A subjective stochastic attitude, by contrast, is not constrained in such a way. From a normative perspective, agents are free to believe as they see fit, as long as they comply to the probability axioms. Statistical theories. For present concerns, the important point is that each of the epistemic interpretations of probability calculus comes with its own set of foundational programs for statistics. On the whole, epistemic probability is most naturally associated with Bayesian statistics, the second major theory of statistical methods. The key characteristics of Bayesian statistics flows directly from the epistemic interpretation. Under this interpretation, it becomes possible to assign probability to a statistical hypothesis and to relate this probability understood as an expression of how strongly we believe the hypothesis to the probabilities of events. Bayesian statistics allows us to express how our epistemic attitudes towards a statistical hypothesis, be it logical, decision theoretic, or stochastic, changes under the impact of data. The take-home message is that the Bayesian method allows us to express our epistemic attitudes to a statistical hypothesis in terms of a probability assignment, and that the data impact on this epistemic attitude in a regulated fashion. It should be emphasized that Bayesian statistics is not the sole user of the epistemic notion of probability. Indeed, a frequentist understanding of probability assigned to statistical hypothesis seems nonsensical, but it is perfectly possible to read the probabilities of events or elements in sample space as epistemic quite independently of the statistical method that is being used. As further explained in the next section, several philosophical developments of classical statistics employ epistemic probability, most notably fiduciary probability, likelihoodism, and evidential probability, or connect to the procedures of classical statistics to inference and support in some other ways. In all of these developments, probabilities and functions over sample space are read epistemically as expressions of the strength of evidence, the degree of support, or similar. Classical statistics. The collection of procedures that may be grouped under classical statistics is vast and multifaceted. By and large, classical statistics procedures share the feature that they only rely on probability assignment over sample spaces. As indicated, an important motivation for this is that those probabilities can be interpreted as frequencies from which the term of frequentist statistics originates. Classical statistics procedures are typically defined by some function over sample space, where this function depends often exclusively on the distribution that the hypothesis under consideration assigned to the sample space. For the range of samples that may be obtained, the function then points to one of the hypotheses, or perhaps to a set of them, as being in some sense the best fit with the sample, or conversely, it discards candidate hypotheses that render the sample too improbable. In some classical procedures employ the data to narrow down a set of hypotheses. Put in such general terms, it becomes apparent that classical procedures provide a response to the problem of induction. The data are used to get from a weak general statement about the target system to a stronger one, namely from a set of candidate hypotheses to a subset of them. The central concern of the philosophy of statistics is how we are to understand these procedures and how we might justify them. Notice that the pattern of classical statistics resembles that of eliminative induction. In view of the data, we discard some of the candidate hypotheses. Indeed, classical statistics is often seen in loose association with Popper's falsification, but this association is somewhat misleading. In classical procedures, statistical hypotheses are discarded when they render the observed sample too improbable, which of course differs from discarding hypotheses that deem the observed sample impossible. Basics of classical statistics. On the basis of Barnett 1999 as primary source, the following focuses on two very central procedures: hypothesis testing and estimation. The first has to do with the comparison of two statistical hypotheses and invokes the theory developed by Neyman and Pearson. The second concerns the choice of a hypothesis from a set and employs procedures devised by Fisher. While these figures are rightly associated with classical statistics, their philosophical views diverge. Hypothesis testing. The procedure of Fisher's null hypothesis test: let H be the hypothesis of interest and let S be a finite sample space. The hypothesis H imposes a distribution over the sample space denoted by P sub H. Every point S in the space represents a possible sample of data. We now define the function F on the sample space that identifies when we will reject the null hypothesis. This expression is often called the likelihood of the hypothesis of the sample. We can set the threshold for the likelihood to a suitable value such that the total probability of the region of rejection is below a given level of error, for example, 5%. It soon appeared that the comparisons between two rival hypotheses were far more informative, in particular because little can be said about error rates if the null hypothesis is in fact false. Neyman and Pearson devised the so-called likelihood ratio test, a test that compares the likelihood of two rivaling hypotheses. The decision to accept or reject a hypothesis is associated with the so-called significance and power of the test. The significance is the probability, according to the null hypothesis, of obtaining data that leads us to falsely reject this hypothesis. The probability alpha is alternatively called the type 1 error, and it is often denoted as the significance or the p-value. The power is the probability, according to the alternative hypothesis, of obtaining data that leads us to correctly reject the null hypothesis. The probability beta is called the type 2 error, or of falsely accepting the null hypothesis. An optimal test is one that minimizes both errors, type 1 and 2. In their fundamental lemma, Nyman and Pearson prove that the decision has optimal significance and power for and only for likelihood ratio test functions. That is, an optimal test depends only on a threshold for the ratio. The threshold of 5% significance is part of a statistical convention and very often fixed before even considering the power. Notice that the statistical procedure associates expected error rates with the decision to reject or accept. Especially Nyman has become known for interpreting this as strictly behaviorist fashion. Estimation. In this section, we briefly consider parameter estimation by maximum likelihood as first devised by Fisher in 1956. While in the foregoing we used a finite sample space, we now employ a space with infinitely many possible samples. Accordingly, a probability distribution over sample space is written down in terms of the so-called density function, which technically speaking expresses the infinitely small probability assigned to an indefinitely small patch around the point. This probability density works much like an ordinary probability function. Maximum likelihood estimation, or MLE for short, is a tool for determining the best among a set of hypotheses, often called a statistical model. There are several requirements that we might impose on an estimator function. One is that the estimator must be consistent. This means for the larger samples of the estimator function converges to the parameter values associated with the distribution of the data generating system, or the true parameter values for short. Another requirement is the estimator must be unbiased, meaning that there is no discrepancy between the expected value of the estimator and the true parameter values. The maximum likelihood estimation procedure is certainly not the only one used for estimating the value of a parameter of interest on the basis of statistical data. A simpler technique is minimization of a particular target function, the minimization of a sum of the squares of the distance between the prediction of the statistical hypothesis and the data points, also known as the method of least squares. A more general perspective, first developed by Wald in 1950, is provided by measuring the discrepancy between the predictions of the hypothesis and the actual data in terms of a loss function. The sum squares and the likelihoods may be taken as expressions of this loss. Often, the estimation is coupled to a so-called confidence interval. There are, of course, many more procedures for estimating a variety of statistical targets, and there are many more expressions for the quality of the estimation. Theories of estimation often come equipped with a rich catalog of situation-specific criteria for estimators reflecting the epistemic and pragmatic goals that the estimator helps achieving. However, it is in itself the estimator functions do not present guidelines for belief, and importantly, confidence intervals do not either. Problems for classical statistics. Classical statistics is widely discussed in the philosophy of statistics. In what follows, two problems with the classical approach are outlined, to wit, its problematic inference with belief and the fact that it violates the so-called likelihood principle. Many more specific problems can be seen to derive from these general ones. Interface with belief. Consider the likelihood ratio test of Nyman and Pearson's. As indicated, the significance or p-value of a test is an error rate that will manifest if data collection and testing is repeated. Assuming that the null hypothesis is in fact true, notably the p-value does not tell us anything about how probable the truth of the null hypothesis is. However, many scientists do use hypothesis testing in this manner, and there is much debate over what can and cannot be derived from a p-value. After all, the test leads to the advice to either reject the hypothesis or accept it, and this seems conceptually very close to giving a verdict of truth or falsity. While the evidential value of p-values is much debated, many admit that the probability of data according to the hypothesis cannot be used straightforwardly as an indication of how believable the hypothesis is. Such usage runs into the so-called base rate fallacy. In short, it seems wrong-headed to turn the results of classical statistics procedures into beliefs. It is a matter of debate whether any of this can be blamed on classical statistics. Initially, Neiman was empathetic to the procedures. Their procedures could not be taken as inferences or as some other way to pertaining to the epistemic status of the hypothesis. Their own statistical philosophy was strictly behavioralist, and it may be argued that the problems disappear if only scientists abandon their faulty epistemic use of classical statistics. As explained in the foregoing, we can uncontroversially associate error rates with classical procedures, and so with the decisions that flow from these procedures. Hence, a behavioralist and error-based understanding of classical statistics seems just fine. However, both statisticians and philosophers have argued that an epistemic reading of classical statistics is possible and, in fact, preferable. Accordingly, many have attempted to reinterpret or develop the theory in order to align it with the epistemically oriented statistical practice of scientists. The nature of evidence. Hypothesis tests and estimations are sometimes criticized because their results generally depend on the probability function over the entire sample space and not exclusively on the probabilities of the observed sample. That is, the decision to accept or reject the null hypothesis depends not on just on the probability of what has actually been observed according to the various hypotheses, but also on the probability assignment over events that could have been observed but were not. Statistics should tell us the objective impact that the data have on hypothesis, but the impact seems to depend on the sampling plan of the researcher and not just on the data themselves. Some will find this dependence unacceptable. The intentions and plans of the researchers are irrelevant to the evidential value of the data, while others argue that it is just right. They maintain that the impact of data on the hypothesis should depend on the stopping rule or protocol that is followed in obtaining it, and not only the likelihoods of the hypothesis have for those data. The motivating intuition is that upholding the irrelevance of the stopping rule makes it impossible to ban opportunistic choices in data collection. In fact, defenders of classical statistics turn the table on those who maintain that optional stopping is irrelevant. They submit that it opens up the possibility of reasoning to a foregone conclusion by, for example, persistent experimentation. We might decide to cease experimentation only if the preferred result is reached. However, as known in Cadane 1996 and further discussed in Steele 2012, persistent experimentation is not guaranteed to be effective as long as we make sure to use the correct, in this case, Bayesian procedures. The debate over optional stopping is evidently concerned with the appropriate evidential impact of data. The central concern in the wider debate is the so-called likelihood principle. This principle has it that the likelihoods of hypothesis for the observed data complexly fix the evidential impact of those data on the hypothesis. In this formulation of Berger and Wolpert, 1984, the likelihood principle states that the two samples are evidently equivalent exactly when they're equal for all hypotheses under consideration, given some constant. Famously, Birnbaum, 1962, offers a proof of the principle from more basic assumptions. The proof relies on the assumption of conditionality. The conditionality principle states that the second sample has the same evidential impact as the first one. What we could have found but did not find has no impact on the evidential value of the sample. Recently, Mayo, 2010, has taken issue with Birnbaum's derivation of the likelihood principle. The classical view sketched above entails a violation of this. The impact of the observed data may be different depending on the probability of other samples than the observed one, because those other samples come into play when determining regions of acceptance and rejection. The Bayesian procedure, on the other hand, uphold the likelihood principle in determining the posterior distribution over hypothesis. Only the prior and the likelihood of the observed data matter. In the debate over optional stopping and in many of the other debates between classical and Bayesian statistics, the likelihood principle is the focal point. Excursion, optional stopping. The view that the data reveal more or something else than what is expressed by the likelihoods of the hypothesis at issue merits detailed attention. It is instructive to consider why exactly the impatient researcher can reject the null hypothesis. This exemplifies that the results of a classical statistical procedure do not only depend on the likelihoods for the actual data, which are indeed the same for both researchers, they also depend on the likelihoods for the data that we did not obtain. Responses to criticism. There have been numerous responses to the above criticism. Some of these responses effectively reinterpret the classical statistical procedures as pertaining only to the evidential impact of data. Other responses developed the classical statistical theory to accommodate the problems. Their common core is that they establish or at least clarify the connection between two conceptual realms. The statistical procedures refer to the physical probabilities, while their results pertain to the evidence and support, and even to the rejection or acceptance of hypotheses. The strength of evidence. Classical statistics is often presented as providing us with advice for actions. The error probabilities do not tell us what epistemic attitudes to take on the basis of statistical procedures. Rather, they indicate the long-run frequency of error if we live by them. Specifically, Neiman advocated this interpretation of classical procedures. Against this, Fisher, Pearson, and other classical statisticians have argued for more epistemic interpretations, and many more recent authors have followed suit. Central to the above discussion on classical statistics is the concept of likelihood, which reflects how the data bears on the hypothesis at issue. In the works of Hacking 1965, Edwards 72, and more recently Royal in 1997, the likelihoods are taken as a cornerstone for statistical procedures and given epistemic interpretation. They are said to express the strength of the evidence presented by the data or the comparative degree of support that the data give to a hypothesis. Hacking formulates this idea in the so-called law of likelihood. If the sample is more probable on the condition of hypothesis 1 than on 2, then the sample supports hypothesis 1 more than it supports 2. The position of likelihoodism is based on a specific combination of views on probability. On the one hand, it employs probabilities over sample spaces and avoids putting probabilities over statistical hypotheses. It thereby avoids the use of probability that cannot be given a physical interpretation. On the other hand, it does interpret the probabilities over sample space as components of a support relation, and thereby as pertaining to the epistemic rather than the physical realm. Notably, the likelihoodist approach fits well with the long history in formal approaches to epistemology, in particular with confirmation theory, in which the probability theory is used to spell out confirmation relations between data and hypothesis. Measures of confirmation invariably take the likelihoods of hypothesis as input components. They provide a quantitative expression of the support relations described by the law of likelihood. Another epistemic approach to classical statistics is presented by Mayo and Spanos, 2011. Over the past decade or so, they have done much to push the agenda of classical statistics in the philosophy of science, which had become dominated by Bayesian statistics. Countering the original behaviorist tendencies of Neiman, the error statistical approach advances an epistemic reading of classical test and estimation procedures. Mayo and Spanos argue that classical procedures are best understood as inferential. They license inductive inferences, but they readily admit that the inferences are defeasible. They could lead us astray. Classical procedures are always associated with particular error and probabilities, the probability of a false projection or acceptance, or the probability of an estimator falling within a certain range. In the theory of Mayo and Spanos, these error probabilities obtain an epistemic role because they are taken to indicate the reliability of the inference licensed by the procedures. The error statistical approach of Mayo and others comprises a general philosophy of science as well as a particular viewpoint on the philosophy of statistics. We briefly focus on that later, though, through a discussion of the notion of a severe test. The claim is that we gain knowledge of experimental effects on the basis of severely testing hypotheses, which can be characterized by the significance and power. In Mayo's definition, a hypothesis passes a severe test on two conditions. The data must agree with the hypothesis, and the probability must be very low that the data agree with the alternative hypothesis. Ignoring potential controversy over the precise interpretation of agree and low probability, we can recognize the criteria of Neiman and Pearson in these requirements. The test is severe if the significance is low, since the data must agree with the hypothesis, and the power is high, since those data must not agree or else have low probability of agreeing with the alternative. Theoretical developments. Apart from the reinterpretations of the classical statistical procedures, numerous statisticians and philosophers have developed a theory of classical statistics further in order to make good on the epistemic role of its results. We focus on two developments in particular, to wit, fiducial and evidential probability. The theory of evidential probability originates with Keiberg, 1961, who developed a logical system to deal consistently with the results of classical statistical systems. Evidential probability thus falls within the attempts to establish the epistemic use of classical statistics. Haney and Kyberg and Tang present an insightful introduction to evidential probability. The system is based on a version default reasoning. Statistical hypotheses come attached with a confidence level, and the logical system organizes how such confidence levels are propagated in inference, and thus advises which hypothesis to use for predictions and decisions. Particular attention is devoted to the propagation of confidence levels in inference that involve multiple instances of the same hypothesis tagged with different confidences, where those confidences result from diverse data sets that are each associated with particular population. Evidential probability assists in selecting the optimal confidence level and thus in choosing appropriate population for the case under consideration. In other words, evidential probability helps to resolve the reference class problem alluded to. Fiduciary probability presents another way in which classical statistics can be given epistemic status. Fisher developed the notion of fiducial probability as a way of deriving a probability assignment over hypothesis without assuming a prior probability over statistical hypothesis at the outset. The fiduciary argument is controversial and is generally agreed that its applicability is limited to particular statistical problems. Excursion, the fiduciary argument. It is not clear why we should take the distribution as appropriate expression of our belief so that we may support the epistemic interpretation of confidence intervals with it. And so the debate continues. In the end, fiduciary probability is perhaps best understood as a halfway house between the classical and Bayesian view on statistics. Classical statistics grew out of a frequentist interpretation of probability, and accordingly, the probabilities appearing in the classical statistical methods are all interpreted as frequencies of events. Clearly, the probability distribution over hypothesis that is generally generated by a fiducial argument cannot be interpreted in this way, so that an epistemic interpretation of this distribution seems the only option. Bayesian statistics. Bayesian statistical methods are often presented in the form of an inference. The inference runs from a so-called prior probability distribution over statistical hypothesis, which expresses the degree of belief in the hypothesis before data has been collected, to a posterior probability distribution over the hypothesis, which expresses the beliefs after the data have been incorporated. The posterior distribution follows via the axioms of probability theory from the prior distribution of the likelihoods of the hypothesis from the data obtained. The probability of the hypothesis assigned to the data. Bayesian methods thus employ data to modulate our attitude towards a designated set of statistical hypotheses, and in this respect, they achieve the same as classical statistical procedures. Both types of statistics present a response to the problem of induction, but whereas classical procedures select or eliminate elements from the set of hypotheses, Bayesian methods express the impact of data in a posterior probability assignment over the set. This posterior is fully determined by the prior and likelihoods of the hypotheses via the formalism of probability theory. The defining characteristics of Bayesian statistics is that it considers probability distributions over statistical hypotheses as well as over data. It embraces the epistemic interpretation of probability wholeheartedly. Probabilities over hypotheses are interpreted as degrees of belief, as expressions of epistemic uncertainty. The philosophy of Bayesian statistics is concerned with determining the appropriate interpretation of these input components and of the mathematical formalisms of probability itself, ultimately with the aim to justify the output. Notice the general pattern of Bayesian statistical method is that of inductivism. In the cumulative sense, under the impact of data, we move to more and more informed probabilistic opinions about the hypothesis. However, in the following, it will appear that Bayesian methods may be also understood as deductivist in nature. Basic pattern of inference. Bayesian inference always starts from a statistical model, a set of statistical hypotheses. While the general pattern of inference is the same, we treat models with a finite number and a continuum of hypotheses separately and draw parallels with hypothesis testing and estimation, respectively. Finite models. Central to Bayesian methods is a theorem from probability theory known as Bayes' theorem, relative to the prior probability distribution over hypothesis and the probability distributions over sample space for each hypothesis. It tells us what the adequate posterior probability over the hypothesis is. Bayesian statistics is first introduced in the context of a finite set of hypotheses after which a generalization to infinite cases is provided. Assume the prior probability over the hypothesis, further assume the likelihoods, the probability assigned to the data conditional of the hypothesis, then Bayes' theorem determines this famous formulation. Bayesian statistics outputs the posterior probability assignment. This expression goes to the interpretation of an opinion concerning the hypothesis, and the sample has been recorded, accommodated. It is a revised opinion. Further results from Bayesian inference can all be derived from the posterior distribution over the statistical hypothesis. For instance, we can use the posterior to determine the most probable value of the parameter, picking the hypothesis for which the probability assignment is maximal. Continuous model. In many applications, the model is not a finite set of hypotheses, but rather a continuum labeled by a real valued parameter. This leads to some subtle changes in the definition of the distribution over hypothesis and the likelihoods. The prior and the posterior must be written down as a so-called probability density function. The expression is often called the marginal likelihood of the model. It expresses how probable the data is in light of the model as a whole. The posterior probability density provides a basis for conclusions that one might draw from the sample and which are similar to estimations and measures for the accuracy of the estimations. The hypothesis can serve as a Bayesian estimation. In analogy to the confidence interval, we can also define a so-called credal interval or credibility interval from the posterior probability distribution. There are many other ways of defining Bayesian estimations and credal intervals for the theory on the basis of the posterior density. The specific type of estimation of the Bayesian analysis offers can be determined by the demands of the scientist. Any Bayesian estimator will to some extent resemble the maximum likelihood estimator due to the central role of the likelihoods in the Bayesian formalism. However, the output will also depend on the prior probability over the hypothesis, and generally speaking, it will only tend to the maximum likelihood estimator when the sample size tends to infinity. Problems with the Bayesian approach. Most of the controversy over the Bayesian method concerns the probability assignment over hypothesis. One important set of problems surrounds the interpretation of those probabilities as beliefs, as to do with the willingness to act or the like. Another set of problems pertains to the determination of the prior probability assignment and the criteria that might govern it. Interpretations of the probability over hypothesis. The overall question here is how we should understand the probability assigned to a statistical hypothesis. Naturally, the interpretation will be epistemic. The probability expresses the strength of the belief in the hypothesis. It makes little sense to attempt a physical interpretation since the hypothesis cannot be seen as a repeatable event or as an event that might have some tendency of occurring. This leaves open several interpretations of the probability assignment as a strength of belief. One very influential interpretation of probability as degree of belief relates to probability to a willingness to bet against a certain odd. There are several problems with this interpretation of the probability assignment over hypothesis. For one, it seems to make little sense to bet on the truth of a statistical hypothesis because such hypothesis cannot be falsified or verified. Consequently, a betting contract on them will never be cashed. More generally, it is not clear that beliefs about statistical hypotheses are properly framed by connecting them to behavior in this way. It has been argued that this way of framing probability assignments introduces pragmatic considerations on beliefs to do with navigating the world successfully into a setting that is by itself more concerned with belief as a truthful representation of the world. A somewhat different problem is that Bayesian formalism, in particular its use of probability assignments over statistical hypotheses, suggests a remarkably closed-mindedness on part of the Bayesian statistician. The Bayesian formalism requires that we assign a probability distribution over the two hypotheses and further that the probability of the model is 1. It is quite a strong assumption, even of an ideally rational agent, that he is indeed equipped with a real valued function that expresses opinion over the hypothesis. Moreover, the probability assignment over hypothesis seems to entail the Bayesian statistician is certain that the true hypothesis is included in the model. This is an unduly strong claim to which a Bayesian statistician will have to commit at the start of analysis. It sits badly with a broadly shared methodological insight, according to which scientific theory must be open to revisions at all times. In this regard, Bayesian statistics does not do justice to the nature of scientific inquiry, or so it seems. The problem just outlined obtains a mathematically more sophisticated form of the problem that Bayesian expects to be well calibrated. It seems that Bayesian statistical analysis placed unrealistic demands even on an ideal agent. Determination of the prior. For the moment, assume that we can interpret the probability over hypothesis as an expression of epistemic uncertainty. Then how do we determine a prior probability? Perhaps we already have an intuitive judgment on the hypothesis in the model so that we can pin down the prior probability on that basis, or else we might have additional criteria for choosing our prior. However, several serious problems attach to procedures for determining the prior. First, consider the idea that the scientist who runs the Bayesian analysis provides the prior probability themselves. One obvious problem with the idea is that the opinion of the scientist might not be precise enough for a determination of a full prior distribution. It does not seem realistic to suppose that the scientist can transform opinion into a single real value function over the model, especially not if the model itself consists of a continuum of hypotheses. But the more pressing problem is that different scientists will provide different prior distributions, and that these different priors will lead to different statistical results. In other words, Bayesian statistical inference introduces an inevitable subjective component into a scientific method. It is one thing that the statistical result depend on the initial opinion of the scientist, but it may so happen that the scientist has no opinion whatsoever about the hypothesis. How is he supposed to assign a prior probability to the hypothesis then? The prior will have to express ignorance concerning the hypothesis. The leading idea in expressing such ignorance is usually the principle of indifference. Ignorance means that we are indifferent between any pair of hypotheses for a finite number of hypotheses. Indifference means that every hypothesis gets equal probability. For a continuum of hypotheses, indifference means that the probability density function must be uniform. Nevertheless, there are different ways of applying the principle of indifference, and so there are different probability distributions over the hypothesis that can count as expressions of ignorance, like Bertrand's paradox. James provides a very insightful discussion of this riddle and also argues that it may be resolved by relying on invariance of the problem under certain transformations. But the general message for now is the principle of indifference does not lead to a unique choice of priors. The point is not that ignorance concerning a parameter is hard to express in a probability distribution over those values. It is rather that in some cases we do not even know what parameter to use to express our ignorance over. In part, the problem of the subjectivity of Bayesian analysis may be resolved by taking a different attitude to scientific theory and by giving up the ideal of absolute objectivity. Indeed, some will argue that it's just right that the statistical methods accommodate difference of opinion among scientists. However, this response misses the mark if the prior distribution expresses ignorance rather than opinion. It seems harder to defend the rationality of differences of opinion than that stem from different ways of spelling out ignorance. Now, there is also a more positive answer to worries over objectivity based on the so-called convergence results. It turns out that the impact of prior choice diminishes with the accumulation of data, and that in the limit, the posterior distribution will converge to a set, possibly a singleton, of best hypothesis determined by the sampled data and hence completely independent of the prior distribution. However, in the short and medium run, the influence of subjective prior choice remains. Summing up, it remains problematic that Bayesian statistics is sensitive to subjective input. The undeniable advantage of the classical statistical procedures is that they do not need any such input, although arguably the classical procedures are in turn sensitive to choices concerning the sample space. Against this, Bayesian statisticians point to the advantage of being able to incorporate initial opinions into the statistical analysis. Responses to criticism. The philosophy of Bayesian statistics offers a wide range of responses to the problems outlined above. Some Bayesians bite the bullet and defend the essentially subjective character of Bayesian methods. Others attempt to remedy or compensate for the subjectivity by providing objectively motivated means of determining the prior probability or by emphasizing the objective character of the Bayesian formalism itself. Strict but empirically informed subjectivism. One very influential view on Bayesian statistics buys into the subjective of the analysis. So-called personalist or strict subjectivists argue that it is just right that the statistical methods do not provide any objective guidelines pointing to radically subjective sources of any form of knowledge. The problem on the interpretation and choice of the prior distribution are thus dissolved, at least in part. The Bayesian statistician may choose the prior at will, and they are an expression of beliefs. However, It deserves emphasis. The subjectivist view on Bayesian statistics does not mean that all constraints deriving from empirical fact can be disregarded. Nobody denies that if you have further knowledge that imposes constraints on the model or the prior, then those constraints must be accommodated. For example, today's posterior probability may be used as tomorrow's prior in the next statistical inference. The point is that such constraints concern the rationality of belief and not the consistency of the statistical inference per se. Subjectivist views are more prominent among those who interpret probability assignment in a pragmatic fashion. Central to this approach is the work of Savage and De Finetti. Savage, 1962, proposed to axiomatize statistics in tandem with decision theory, a mathematical theory about practical rationality. He argued that by themselves, the probability assignments do not mean anything at all, and that they can be only interpreted in context where an agent faces a choice between actions, a choice among a set of bets. In a similar vein, De Finetti advocates a view on statistics in which only the empirical consequences of the probabilistic beliefs expressed in a willingness to bet mattered, but he did not make statistical inference fully dependent on decision theory. Remarkably, it thus appears that the subjectivist view on Bayesian statistics is based on the same behavioralism and empiricism that motivated Neiman and Pearson to develop classical statistics. Notice that all this makes one aspect of the interpretation problem reappear. How will the prior distribution over hypothesis make itself apparent in behavior so that it can rightfully be interpreted in terms of belief, here understood as a willingness to act? One response to the question is in turn to different motivations for representing degrees of belief by means of probability assignments. Following work by De Finetti, several authors have proposed vindications of probabilistic expressions or belief that are not based on behavioral goals, but rather the epistemic goal of holding beliefs that accurately represent the world. A strong generalization of the ideas achieved by Shkervish, Seidenfeld, and Kadani, 2009, which builds on a longer tradition of using scoring rules for achieving statistical aims. An alternative approach is that any formal representation of belief must respect certain logical constraints. Cox provides an argument for the expression of belief in terms of probability assignments on the basis of the nature of partial belief per se. However, the original subjectivist response to the issue that a prior over hypothesis hard to interpret came from De Finetti's so-called representation theorem, which shows that every prior distribution can be associated with its own set of predictions and hence with its own behavioral consequences. In other words, De Finetti showed how priors are indeed associated with beliefs that can carry a betting interpretation. Excursion, the representation theorem. De Finetti's representation theorem relates rules for predication as functions of the given sample data to Bayesian statistical analysis of those data against the background of a statistical model. See Festa and Sups for useful introductions. De Finetti considers a process that generates a series of time-indexed observation, and he then studies prediction rules that take these finite segments as input and return a probability over future events using a statistical model that can analyze such samples and provide the predictions. The key result of De Finetti is that a particular statistical model, namely the set of all distributions in which the observations are independently and identically distributed, can be equated with the class of exchangeable prediction rules, namely the rules whose predictions do not depend on the order in which the observations come in. Hey, Memes, good to see you. God bless. Representation theorems equate a prior distribution over statistical hypothesis to a prediction rule, and thus the probability assignment that can be given a subjective and behavioral interpretation. This removes the worry expressed above that the prior distribution over hypothesis cannot be interpreted subjectively because it cannot be related to the belief as a willingness to act. Priors relate uniquely to a particular prediction. However, for De Finetti, the representation theorem provided a reason for doing away with statistical hypothesis altogether, and hence the removal of a notion of probability as anything other than subjective opinion. Hypotheses whose probabilistic claim could be taken to refer to intangible chancy processes are superfluous metaphysical baggage. Not all subjectivists are equally dismissive of the use of statistical hypotheses. Jeffrey has proposed the so-called mixed Bayesianism, in which subjectively interpreted distributions over the hypothesis are combined with a physical interpretation of the distribution that hypotheses define over sample space. Romange argues that the priors over hypothesis are efficient and more intuitive way of determining inductive predictions than specifying properties of predictive systems directly. This advantage of using hypotheses seems in agreement with the practice of science in which hypotheses are routinely used and often motivated by mechanistic knowledge on the data generating process. The fact that statistical hypotheses can, strictly speaking, be eliminated does not take away from their utility in making predictions. Bayesian statistics as logic. Despite its seemingly inevitable subjective character, there is a sense in which Bayesian statistics might lay claim to objectivity. It can be shown that the Bayesian formalism meets certain objective criteria in rationality, coherence, and calibration. Bayesian statistics thus answers to the requirement of objectivity at a meta level, while the opinions that it deals with retain a subjective aspect. The way in which it deals with these opinions, in particular the way in which data impacts on them, is objectively correct, or so it is argued. Arguments supporting the Bayesian way of accommodating data, namely conditionalization, have been provided in a pragmatic context by dynamic Dutch book arguments, where probability is interpreted as willingness to bet. An important distinction must be made in arguments that support the Bayesian way of accommodating evidence. The distinction between Bayes' theorem as a mathematical given and Bayes' rule as a principle of coherence over time. The theorem is simply a mathematical relation among probability assignments, and is such not subject to debate. Arguments that support the representation of the epistemic state of an agent by means of probability assignments also provide support for Bayes' theorem as a constraint on degrees of belief. The conditional probability can be interpreted as the degree of belief attached to the hypothesis on the condition that the sample is obtained, and as integral part of the epistemic state captured by the probability assignment. Bayes' rule, by contrast, presents a constraint on probability assignment that represents epistemic states of an agent at different points in time. It determines that the new probability assignment express the epistemic state of the agent after the sample has been obtained is systematically related to the old assignment, representing the epistemic state before the sample came in. In the philosophy of statistics, many Bayesians adopt Bayes' rules implicitly, but in what follows, I will only assume that Bayesian statistical inferences relies on Bayes' theorem. Whether the focus lies on Bayes' rule or Bayes' theorem, the common theme in the above-mentioned argument is that they approach Bayesian statistical inference from a logical angle and focus on its internal coherence and consistency. While its use in statistics is undeniably inductive, Bayesian inference thereby obtains a deductive or at least non-amplitative character. Everything that is concluded in the inference is somehow already present in the premise. In Bayesian statistical inference, these premises are given by the prior over the hypothesis and the likelihood function. As determined for each hypothesis separately, these premises fix a single probability assignment over the space at the outset of the inference. The conclusion and terms are straightforward consequences of the probability assignment. They can be derived by applying theorems of probability theory, most notably Bayes' theorem. Bayesian statistical inference thus becomes an instance of probabilistic logic. Summing up, there are several arguments showing that statistical inferences by Bayes' theorem or by Bayes' rule is objectively correct. These arguments invite us to consider Bayesian statistics as an instance of probabilistic logic. Such appeals to the logicality of Bayesian statistical inference may provide a partial remedy for its subjective character. Moreover, a logical approach to the statistical inferences avoid the problem that the formalism places unrealistic demands on the agents and that it presumes the agent to have certain knowledge. Much like in deductive logic, we need not assume that the inferences are psychologically realistic, nor that the agents actually believe the premises of the arguments. Rather, the arguments present the agents with a normative ideal and take the conditional form of consistency constraints. If you accept the premises, then these are the conclusions. Excursion, inductive logic and statistics. An important instance of probabilistic logic is presented in inductive logic as divided by Carnap, Hintika, and others. Historically, Carnapian inductive logic developed prior to the probabilistic logics referenced above and more or less separately from the debates in the philosophy of statistics. But the logical systems of Carnap can quite easily be placed into the context of logical approaches to Bayesian inferences, and doing this is in fact quite insightful. For simplicity, we choose a setting that is similar to the one used in the exposition of the representation theorem, namely a binary data generating process, a string of zeros and ones. The prediction rule determines a probability for the event that the next bit in the string is 1 on the basis of a given string of bits with a given length. Carnap and the followers design specific exchangeable prediction rules mostly variants of the straight line. Carnap derived such rules from constraints on the probability assignments over the samples. Some of these constraints boil down to the axioms of probability. Other constraints, exchangeability among them, are independently motivated by an appeal to so-called logical interpretations of probability. Under this logical interpretation, the probability assignment must respect certain invariances under transformations of the sample space, in analogy to the logical principles that constrain truth evaluations over a language in a particular way. Carnapian inductive logic is an instance of probabilistic logic because its sequential predictions are all based on a single probability assignment at the outset, and because it relies on Bayes' theorem to adapt the predictions to sample data. One important difference with Bayesian statistical inference is that for Carnap, the probability assignment specified at the outset only ranges over samples and not over hypotheses. However, by Di Finetti's representation theorem, Carnap's exchangeable rules can be equated to a particular Bayesian statistical inference. A further difference is that Carnapian inductive logic gives preferential status to particular exchangeable rules in view of Di Finetti's representation theorem. This comes down to the choice for a particular set of preferred priors. As further developed below, Carnapian inductive logic is thus related to objective Bayesian statistics. It is a moot point whether the further constraints on the probability assignment can be considered as logical, as Carnap and followers have it, or whether the title of logic is best reserved for the probability formalism in isolation, as Di Finetti and others argue. Objective priors. A further set of responses to the subjectivity of Bayesian statistical inference targets the prior distribution directly. We might provide further rationality principles with which the choice of priors can be chosen objectively. The literature proposes several objective criteria for filling in the prior over the model. Each of these lays claim to being the correct expression of complete ignorance concerning the value of the model parameters, or of minimal information regarding the parameters. Three such criteria are discussed here in the context of Bertrand's paradox: the principle of indifference, according to which probability should be distributed evenly over the available possibilities; a further development of the ideas presented by the requirement of that a distribution should have maximum entropy, notably the use of entropy maximization for determining degrees of beliefs, find much broader application than only in statistics. Similar ideas are taken up in diverse fields like epistemology, inductive logic, statistical mechanics, and decision theory. In objective Bayesian statistics, the idea is applied to the prior distribution over the model. For continuous models, the maximum entropy distribution depends crucially on the metric over the parameters in the model. The burden of subjectivity is thereby moved to the parameterization, but of course, it may well be that we have strong reasons for preferring a particular parameterization over others. There are other approaches to the objective determination of priors. In view of the above problems, particularly attractive method for choosing a prior over a continuous model is proposed by Jeffreys, 1961. The general idea, so-called the Jeffreys priors, is that the prior probability assigned to a small patch in the parameter space is proportional to what may be called the density of the distributions within the patch. Intuitively, if a lot of distributions that differ quite a lot among themselves are packed together on the small patch in the parameter space, this patch should be given a larger prior probability than a similar patch within which there is little variation among the distributions. More technically, such a density is expressed by prior distribution that is proportional to the Fisher information. A key advantage of these priors is that they are invariant under reparameterizations of the parameter space. A new parameterization naturally leads to adjusted density of distributions. The final method of defining priors goes under the name of reference priors. The proposal starts from the observation that we should minimize the subjective of the results of our statistical analysis, and hence that we should minimize the impact of the prior probability on the posterior. The idea of reference priors is exactly that it will allow the sample data a maximum say in the posterior distribution, but since at the outset we do not know what sample we will obtain, the prior is chosen so as to maximize the expected impact of the data. The expectation must itself be taken with respect to some distribution over sample space, but again, it may well be that we have strong reasons for the latter distribution. Circumventing priors. A different response to the subjectivity of priors is extended to the Bayesian formalism in order to leave the choice of prior to some extent open. The subjective choice of a prior is in that case circumvented. Two such responses will be considered in some detail. Recall that a prior probability distribution over statistical hypothesis expresses our uncertain opinion on which of the hypotheses is right. The central idea behind hierarchical Bayesian models is that the same pattern of putting a prior over statistical hypothesis can be repeated on the level of priors itself. More precisely, we may be uncertain over which prior probability distribution over the hypothesis is right. If we characterize possible priors by means of a set of parameters, we can express this uncertainty about a prior choice in a probability distribution over the parameters that characterize the shape of the prior. In other words, we move our uncertainty one level up in a hierarchy. We consider multiple priors over the statistical hypothesis and compare the performance of these priors on the sample data as if the priors were themselves hypotheses. The idea of hierarchical Bayesian modeling relates naturally to the Bayesian comparison of Carnapian prediction rules, and also to the estimation of optimum inductive methods. Hierarchical Bayesian modeling can also be related to another tool for choosing a particular prior distribution over hypothesis, namely the method of empirical Bayes, which estimates the prior that leads to a maximal marginal likelihood of the model. In the philosophy of science, hierarchical Bayesian modeling has made a first appearance due to Henderson. There is also a response that avoids the choice of prior altogether. This response starts with the same idea as hierarchical models. Rather than considering a single prior over the hypothesis in the model, we consider a parameterized set of them. But instead of defining a distribution over the set, proponents of the interval valued or imprecise probability claim that our epistemic state regarding the priors is better expressed by this set of distributions, and that sharp probability assignments must therefore be replaced by lower and upper bounds to the assignment. Now, the idea that uncertain opinion is best captured by a set of probability assignments, or a creedal set for short, has a long history and is backed by an extensive literature. In light of the main debate in the philosophy of statistics, the use of interval-valued priors indeed forms an attractive extension of Bayesian statistics. It allows us to refrain from choosing a specific prior and thereby presents a reapproachment to the classical view on statistics. These theoretical developments may look attractive, but the fact that they mostly enjoy a cult status among philosophers of statistics, and that they have not moved the statistician in the street, moved to the statistician in the street. On the other hand, standard Bayesian statistics has seen a steep rise in popularity over the past decade or so, owing to the availability of good software and numerical approximation methods, and most of the practical use of Bayesian statistics is more or less insensitive to the potentially subjective aspects of statistical results, employing uniform priors as a neutral starting point for the analysis and relying on the aforementioned convergence results to wash out the remaining subjectivity. However, this practical attitude of scientists towards modeling should not be mistaken for a principled answer to the questions raised in the philosophy of statistics. AKL, God bless, good to see you. Statistical methods. In the foregoing, we have seen how classical and Bayesian statistics differ, but the two major approaches to the statistics have also a lot in common. Most importantly, all statistical procedures rely on the assumption of a statistical model, here referring to any restricted set of statistical hypotheses. Moreover, they are both aimed at delivering a verdict over these hypotheses. For example, in a classical likelihood ratio, tests consider two hypotheses and then offer a verdict of rejection and acceptance, while a Bayesian comparison delivers a posterior probability over these two hypotheses. Whereas in Bayesian statistics, the model presents a very strong assumption. Classical statistics does not endow the model with special epistemic status. They are simply the hypothesis currently entertained by the scientists, but across the board, the adoption of a model is absolutely central to any statistical procedure. A natural question is whether anything can be said about the quality of the statistical model and whether any verdict on the starting point for statistical procedures can be given. Surely some models will lead to better predictions or be a better guide to the truths than others. The evaluation of models touches on deep issues in the philosophy of science because the statistical model often determines how the data generating system under investigation is conceptualized and approached. Model choice thus resembles the choice of a theory, a conceptual scheme, or even a whole paradigm, and thereby might seem to transcend the formal frameworks for studying theoretical rationality. Despite the fact that some considerations on model choice will seem extra statistical in the sense that they fall outside of the scope of statistical treatment, statistics offers several methods for approaching the choice of statistical models. Model comparisons. There are in fact very many methods for evaluating statistical models. In first instance, the methods occasions comparisons of statistical models, but very often they are used for selecting one model over the other, Others, in what follows, we only review prominent techniques that have led to philosophical debate: Ikake's information criterion, the Bayesian information criterion, and furthermore, the computation of marginal likelihoods and posterior model probabilities, both associated with Bayesian model selection. We leave aside methods that use cross validation, as they have unduly not received as much attention in the philosophical literature. Ikake's information criteria. Ikake's information criteria, modestly termed an information criterion, or AIC for short, is based on the classical statistical procedure of estimation. It starts from the idea that a model can be judged on the estimate that it delivers, and more specifically by the proximity of the estimate to the distribution with which the data are actually generated, the true distribution. The proximity is often equated with the expected predictive accuracy of the estimate, because if the estimate and the true distribution are closer to each other, their predictions will be better aligned to one another as well. In the derivation of the information criterion, the so-called relative entropy or Kullback-Leibler divergence of the two distributions is used to measure their proximity, and hence as a measure of the expected predictive accuracy of the estimate. Naturally, the true distribution is not known to the statistician who is evaluating the model. If it were, then the whole statistical analysis would be useless. However, it turns out that we can give an unbiased estimation of the divergence between the two distributions and the distribution estimated from a particular model, the maximum likelihood estimate of the model, thereby features in an expression of the model quality in a role that is conceptually distinct from the estimator function. As can be seen from the expression above, a model with a smaller information criterion is preferable. We want the fit to be optimal at little cost and complexity. Notice that the number of dimensions or independent parameters in the model increases the information criteria and thereby lowers the eligibility of the model. If two models achieve the same maximum likelihood for the sample, then the model with fewer parameters will be preferred. For this reason, statistical model selection by the information criterion can be seen as an independent motivation for preferring simple models over more complex ones. But this result also invites some critical remarks. For one, we might impose other criterion than merely the unbiasedness on the estimation of proximity to the truth, and this will lead to different expressions for the approximation. Moreover, it is not always clear-cut what the dimensions of the model under scrutiny really are. For curve fitting, this may seem simple, but for more complicated models or different conceptualizations of the space of models, things do not look so easy. A prime example of model selection is presented in curve fitting. A Life 101, God bless. Bayesian evaluation of models. Various other prominent model selection tools are based on the methods from Bayesian statistics. They all start from the idea that the quality of a model is expressed in the performance of the model on the sample data. The model that, on the whole, makes the sample data most probable is to be preferred. Because of this, there is a close connection with the hierarchical Bayesian model referred to earlier. The central notion is the Bayesian model selection tools is thus the marginal likelihood of the model, the weighted average of the likelihoods over the model, using the prior distribution of a weighting function. The marginal likelihood can be combined with the prior probability over models to derive the so-called posterior model probability using Bayes' theorem. One way of evaluating models, known as Bayesian model selection, is by comparing the models on their marginal likelihood or else on their posteriors. Usually the marginal likelihood cannot be computed analytically. Numerical approximations can often be obtained, but for practical purposes it is proved very useful and quite sufficient to employ an approximation of the marginal likelihoods. This approximation has become known as Bayesian information criterion. The occurrence of the information criterion and the Bayesian information criterion seem to give a further motivation for our intuitive preference for simple models over more complex ones. Indeed, other model selection tools like the deviance information criterion and the approach based on the minimum description length also result in expressions that feature a term that penalizes complex models. However, this is not to say that the dimensions term that we know from the information criteria exhausts the notion of model complexity. There is ongoing debate in the philosophy of science concerning the merits of model selection and explications of the notion of simplicity, informativeness, and the like. Statistics without models. There are also statistical methods that refrain from the use of a particular model by focusing exclusively on the data or by generalizing over all possible models. Some of these techniques are properly localized in descriptive statistics. They do not concern an inference from data, but merely serve to describe the data in a particular way. Statistical methods that do not rely on an explicit model choice have unfortunately not attracted much attention in the philosophy of statistics, but for completeness' sake, they will be briefly discussed here. Data reduction techniques. One set of methods, and quite important one for many practicing statisticians, is aimed at data reduction. Often the sample data are very rich, consisting of a set of points in a space of very many dimensions. The first step in a statistical analysis may then be to pick out the salient variability in the data in order to scale down the computation burden of the analysis itself. The technique of the principal component analysis, PCA, is designed for this purpose. Given a set of points in a space, it seeks out the set of vectors along which the variation in the points is large. Principal component analysis is only one item from a large collection of techniques that are aimed at keeping the data manageable and finding patterns in it, a collection that also includes kernel methods and support vector machines. For present purposes, it is important to stress that such tools should not be confused with statistical analysis. They do not involve the testing or evaluation of distributions over sample space, even though they build up and evaluate models of the data. This sets them apart from confirmation and exploratory factor analysis, which is sometimes taken to be a close relative of principal component analysis, because both sets of techniques allow us to identify salient dimensions within the sample space, along with which the data show large variation. Practicing statisticians often employ data reduction tools to arrive at conclusions on the distributions from which the data were sampled. There is already a wide use for machine learning and data mining techniques in the sciences, and we may expect even more even mode usage of these techniques in the future because so much data is now coming available for scientific analysis. However, in the philosophy of statistics, there is little debate yet over the epistemic status of conclusions reached by means of these techniques. Philosophers of statistics would do well to direct some attention here. Formal learning theory. An entirely different approach to statistics is presented by formal learning theory. This is again a vast area of research, primarily located in computer science and artificial intelligence. The discipline is here mentioned briefly as another example of an approach to statistics that avoids the choice of statistical model altogether and merely identifies patterns in the data. We leave aside the theory of neural networks, which also concerns predictive systems that do not rely on statistical model, and focus on the theory of learning algorithms because of all of these approaches, they have seen most philosophical attention. Pioneering work on formal learning was done by Solomonov in 1964. As before, the setting is one in which the data consists of a string of zeros and ones, and in which the agent is attempting to identify the pattern in the data. The central idea of Solomonov is that all possible computable patterns must be considered by the agent, and therefore that no restrictive choice on statistical hypothesis is warranted. Solomonov then defined a formal system in which indeed all patterns can be taken into consideration effectively using a Bayesian analysis with a cleverly constructed prior overall computable hypothesis. This general idea can be identified in a rather new field of the intersection of Bayesian statistics and machine learning, Bayesian nonparametrics. Rather than specifying at the outset a confined set of distributions from which a statistical analysis is supposed to choose on the basis of the data, the idea is that the data are confronted with a potentially infinite dimensional space of possible distributions. The set of distributions taken into consideration is then made relative to the data obtained. The complexity of the model grows with the sample. The result is a predictive system that performs an outline model selection alongside a Bayesian accommodation of the posterior over the model. Current formal learning theory is a lively field to which philosophers of statistics also contribute. Particular salient for the present concern is that the system of formal learning are set up to achieve some notion of adequate universal prediction without confining themselves to a specific set of hypotheses, and hence by imposing a minimal constraint on the set of possible patterns in the data. It is a matter of debate whether this is at all possible and to what extent the predictions of formal learning theory thereby rely on implicit assumptions on the structure of the sample space. Philosophical reflection on this is only in its infancy. Related topics. There are numerous topics in the philosophy of science that bear direct relevance to the themes covered in this lemma. A few central topics are mentioned here to direct the reader to related lemmas in this encyclopedia. One very important topic that is immediately adjacent to the philosophy of statistics is confirmation theory, the philosophical theory that describes and justifies relationships between scientific theory and empirical evidence. Arguably, the theory of statistics is a proper part of confirmation theory, as it describes and justifies the relationship that obtains between statistical theory and evidence in the form of samples. It can be insightful to place statistical procedures in this wider framework of relations between evidence and theory. Zooming out even further, the philosophy of statistics is part of the philosophical topic of methodology, the general theory on whether and how science acquires knowledge. Thus, conceived statistics is one component in a large collection of statistical methods comprising concept formation, experimental design, manipulation, and observation, confirmation, revision, and theorizing. There are also a fair number of specific topics in the philosophy of science that are spelled out in terms of statistics, or that are located in close proximity to it. One of these topics is the process of measurement, in particular the measurement of latent variables on the basis of statistical facts about manifest variables. The so-called representation theory of measurement relies on statistics, in particular on factor analysis, to provide a conceptual clarification on how mathematical structures represent empirical phenomenon. Another important topic from the philosophy of science is causation. Philosophers have employed probabilistic theory to capture causal relations ever since Reichenbach, 1956, but more recent work on causality in statistics has given the theory of probabilistic causality an enormous impulse. Here again, statistics provides a basis for the conceptual analysis of causal relations, and there is so much more. Several specific statistical techniques like factor analysis and the theory of Bayesian networks invite conceptual discussions of their own accord. Numerous topics within the philosophy of science lend themselves to statistical elucidation, the coherence, informativeness, and surprise of evidence, and in turn there is a wide range of discussions in the philosophy of science that inform a proper understanding of statistics. Among them are debates over experimentation and intervention, concepts of chance, the nature of scientific models, and theoretical terms. The reader is invited to consult the entries on the topics to find further indications of how they relate to the philosophy of statistics. Okay, so that one was really long and pretty important. So last but not least, we have computational philosophy. I'm just going to take a quick drink. And for the multiple truth hypothesis, statistics is extremely important because it also has an aspect of the truth discovery function that will give a value, which would be a statistical value of a probability of various truths, and different truths would have a value between 0 and 1 for the probability of them being true, in the sense of like the Dutch, like the bet or decision theory. So let me just pour myself a quick cup of tea, and then we'll finish up with computational philosophy, which will be shorter. Hey, Rune, God bless. Good to see you. Okay, so this is the last one from the Philosophy of Science series. Obviously, there's more that could have been covered, but this would be a pretty comprehensive introduction, even intermediary, and people who follow Week in Review will go in, we have already, and will go in more detail into some of these concepts. and from there to metaphysics. So this one's pretty interesting and fun, and has a lot to do with modern machine learning. Although I'm leaving out the examples and the technical parts, so it'll be quicker. Computational philosophy. Computational philosophy is the use of mechanized computational techniques to instantiate, extend, and amplify philosophical research. Computational philosophy is not philosophy of computers or computational techniques. It is rather a philosophy using computers and computational techniques. The idea is simply to apply advances in computer technology and techniques to advance discovery, exploration, and arguments within any philosophical area. After touching on the historical precursors, this article discusses contemporary computational philosophy across a variety of fields: epistemology, metaphysics, philosophy of science, ethics and social philosophy, philosophy of language, and philosophy of mind, often with examples of operating software. Far short of any attempt at an exhaustive treatment, the intention is to introduce the spirit of each application by using some representative examples. Introduction. Computational philosophy is not an area or subdiscipline of philosophy, but a set of computational techniques applicable across many philosophical areas. The idea is to simplify, to apply computational modeling and techniques to advance philosophical discovery, exploration, and argument. One should not therefore expect a sharp break between computational and non-computational philosophy, nor a sharp break between computational philosophy and other computational disciplines. The past half century has seen impressive advances in raw computer power, as well as theoretical advances in automated theorem proving, agent-based modeling, causal and system dynamics, neural networks, machine learning, and data mining. What might contemporary computational technologies and techniques have to do offer in advancing our understanding of issues in epistemology, ethics, social and political philosophy, philosophy of language, philosophy of mind, philosophy of science, or philosophy of religion, suggested by Leibniz, and with important precursors in the history of formal logic. The idea is to apply new computational advances within long-standing areas of philosophical interest. Computational philosophy is not the philosophy of computation, an area that asks about the nature of computation itself. Although applicable and informative regarding artificial intelligence, computational philosophy is not the philosophy of artificial intelligence, nor is it an umbrella term for the questions about the social impact of computer use explored, for example, in the philosophy of information, philosophy of technology, and computer ethics. More generally, there is no of that computational philosophy can be said to be the philosophy of computational philosophy, represents not an isolated topic area, but the widespread application of whatever computer techniques are available across the full range of philosophical topics. Techniques employed in computational philosophy may draw from a standard computer programming and software engineering, including aspects of artificial intelligence, neural networks, system science, complex adaptive systems, and a variety of computer modeling methods. As a growing set of methodologies, it includes the prospect of computational textual analysis, big data analysis, and other techniques as well. Its field of application is equally broad, unrestricted within the traditional discipline and domain of philosophy. This article is an introduction to the computational philosophy rather than anything like a complete survey. The goal is to offer a handful of suggestive examples across the computational techniques and field of philosophical application. Anticipations in Leibniz. The only way to rectify our reasonings is to make them as tangible as those of mathematicians, so that we can find our error at a glance. And when there are disputes among persons, we can simply say, let us calculate without further ado to see who is right. Leibniz started discovery in 1685. Formalizations of philosophical argument has a history as old as logic. Logic is the historical source and foundation of contemporary computing. Our topic here is more specific, the application of contemporary computing to a range of philosophical questions, but that too has a history evident in Leibniz's version of the power of computation. Leibniz is known for both the development of formal techniques in philosophy and the design and production of actual computational machinery. In 1642, the philosopher Blaise Pascal had invented the Pascaline, designed to add with, carry, and subtract. Between 1673 and 1720, Leibniz designed a series of calculating machines intended to instantiate multiplication and division as well, a stepped reckoner employing what is still known as the Leibniz wheel. The sole surviving Leibniz step reckoner was discovered in 1879 as a workman was fixing a leaking roof at the University of Göttingen. In correspondence, Leibniz alluded to a cryptographic encoder and decoded using the same mechanical principles. On the basis of these descriptions, Nicholas Rescher has produced a working conjecture reconstruction. But Leibniz had visions for the power of computation far beyond mere arithmetic and cryptography. Leibniz, 1966, Dissertatio de Arte Combinatoria, trumpets the art of combinations as a method of producing novel ideas and inventions, as well as analyzing complex ideas into simpler elements. Leibniz describes it as the mother of inventions that would lead to a discovery of all things, with applications in logic, law, medicine, and physics. The vision was a set of formal methods applied within a perfect language of pure concepts, which would make possible the general mechanization of reason. The specifics of Leibniz's combinatorial vision can be traced back to the mystical mechanisms of Raymond Lull circa 1308, a combinatorial mechanism lampooned in Jonathan Swift's Gulliver's Travels of 1726 as allowing one to write books in philosophy, poetry, politics, mathematics, and theology without the least assistance from genius or study. Combinatorial specifics aside, however, Leibniz's vision of an application of computational methods to substantive questions remain. It is the vision of computational physics, computational biology, computational social science, and an application to perennial questions within philosophy of computational philosophy. Computational philosophy by example. Despite Leibniz's hope for a single computational method that would serve as a universal key to discovery, computational philosophy today is characterized by a number of distinct computational approaches to a variety of philosophical questions. Particular questions and particular areas have simply seemed ripe for various methods, methodologies, or techniques. Both attempts and results are therefore scattered across a range of different areas. In what follows, we offer a survey of various explorations in computational philosophy. Social epistemology and agent-based modeling. Computational philosophy is perhaps most easily introduced by focusing on applications of agent-based modeling to question in social epistemology, social and political philosophy, philosophy of science, and philosophy of language. Sections 3.1 through 3.3 are therefore structured around examples of agent-based modeling in these areas. Other important computational approaches and other areas are discussed in sections 3.4 through 3.6. Traditional epistemology, the epistemology of Plato, Hume, Descartes, and Kant, treats the acquisition and validation of knowledge on the individual level. The question for traditional epistemology was always how I, as an individual, can acquire knowledge of the objective world when all I have to work with is my subjective experience. Perennial questions of individual epistemology remain, but the last few decades have seen the rise of a very different form of epistemology as well, anticipated in the early work of Alvin Goldman, Helen Longino, Philip Kitcher, and Miriam Solomon. Social epistemology is now evident within dedicated journals and across philosophy quite generally. I acquire my knowledge of the world as a member of a social group, a group that includes those inquirers that constitute the scientific enterprise. For example, in order to understand the acquisition and validation of knowledge, we have to go beyond the level of individual epistemology. We need to understand the social structure, dynamics, and process of scientific investigation. It is within this social turn in epistemology that the tools of computational modeling, agent-based modeling in particular, become particularly useful. The following two sections use computational work on belief change as an introduction to agent-based modeling in social epistemology. Belief change and opinion polarization. How should we expect beliefs and opinions to change within a social group? How might they rationally change? The computational approach to these kinds of questions attempts to understand the basic dynamics of the target phenomenon by building, running, and analyzing simulations. Simulations may start with a model of interactive dynamics and initial conditions, which might include, for example, the initial beliefs of individual agents and how prone those agents are to share information and listen to others. The computer calculates successive states of the model steps as a function, typically stochastic, of preceding stages. Researchers collect and analyze simulation outputs, which might include, for example, the distribution of beliefs in the simulated society after a certain number of rounds of communication. Because simulations typically involve many stochastic elements, which agents talk with which agents at which point in the simulation, what specific beliefs specific agents start with, etc. Data is usually collected and analyzed across a large number of simulation runs. One model of belief change and opinion polarization that has been of wide interest is that of Hegselman and Krauss, which offers a clear and simple example of the application of agent-based techniques. Opinions in the Hegselman and Krauss model are mapped as numbers in the 0-1 interval, with initial opinions spread uniformly at random in an artificial population. Individuals update their beliefs by taking an average of the opinion that are close enough to the agent's own. As agents' beliefs change, a different set of agents or a different set of values can be expected to influence further updating. A crucial parameter in this model is the threshold of what counts as close enough for actual influence. Encourage people to read through these examples on their own. The topic of polarization is anticipated in an earlier tradition of cellular autonomous models initiated by Robert Axelrod. The basic premise of Axelrod is that people tend to interact more with those like themselves and tend to become more like those with whom they interact. But if people come to share one another's beliefs or other cultural features over time, why do we not observe complete cultural convergence? At the core of Axelrod's model is a spatially instantiated imitative mechanism that produces cultural convergence within local groups, but also results in progressive differentiation and cultural isolation between groups. The social dynamics of argument. In general, the social dynamics of belief change reviewed above treats beliefs as items that spread by contact, much on the model of infection dynamics. Other attempts have been made to model belief change in greater detail, motivated by reasons or arguments, with gestures towards earlier works by Plan Ming Dung and Gregor Betts, 1995, constructs a model of belief change based on a dialectic structures of linked arguments. Sentences and their negations are represented as digits, positive and negative, arguments as ordered sets of sentences, and two forms of links between arguments: an attack relation in which a conclusion of one argument contradicts the premise of another, and supports a relation in which the conclusion of one argument is equivalent to the premise of another. A position on a dynamical structure, complete or partial, consists of an assignment of truth values T or F to the elements of the set of sentences involved. Consistent positions relative to a structure are those in which contradictory sentences are assigned opposite truth values, and every element argument in which all premises are assigned T has a conclusion which is assigned T as well. Betts then maps the space of coherent positions for a different dialectical structure as an undirected network with links between positions that differ in truth value of just one sentence of the set. Arguments are added randomly, starting from a blank slate, and agents move to the coherent position closest to the previous position with a random choice in the case of a draw. In variations of the basic structure, Betts considers cases in which an initial background agreement is assumed cases of controversial argumentation in which arguments are introduced which support a proponent's position or attack an opponent's, and in which up to 6 agents are involved. In 2 series of simulation, he tracks both the consensus conduciveness of different parameters and with an assumption of a specific assignment as the truth conduciveness of different parameters. In individual runs, depending on initial positions and arguments introduced, Betts finds that argumentation of the sort modeled can either increase or decrease agreement and contract the truth or lead astray. Averaging across many debates, however, Betts finds that the controversial argumentation in particular is both consensus conducive and better tracks the truth. Computational philosophy of science. Computational models have been used in the philosophy of science in 2 very different respects: as models of scientific theory and as models of the social interaction characteristics of collective scientific research. The next section reviews some examples of each. Network models of scientific theory. Computational philosophy of science is enshrined in a book title as early as Paul Thagard's 1988. A central core of his work is a connection echo program, which constructs a network structure as a scientific explanation from inputs of explain, contradict, data, and analogous from the status and relation of nodes. Echo uses a set of principles of explanatory coherence to construct a network of undirected excitatory and inhibitory links between nodes which cohere with those which incohere respectively. Starting with the initial node activations close to zero, the nodes of the coherence networks are synchronously updated in terms of their old activation and weighted input from linked nodes, which data node set at a constant input of 1. Once the network settles down to equilibrium, an explanatory hypothesis is taken to defeat another if its activation value is higher, at least positive as opposed to negative. The guard is able to show that such an algorithm effectively echoes a range of familiar observations regarding theory selection. Hypotheses that explain more defeat those that explain less. For example, and simpler hypotheses are to be preferred. In contrast to simple Popperian refutation, Echo abandons a hypothesis only when a dominating hypothesis is available. The guard uses a basic approach of explanatory coherence, instantiated in Echo, in an analysis of a number of historical cases in the history of science, including the abandonment of phlogiston theory in favor of oxygen theory, the Darwinian Revolution, and the eventual triumph of Wegener's plate tectonics and continental drift. The influence of Bayesian networks has been far more widespread, both across disciplines and the technical logical application made possible only with computers. Grounded in the work of Judah Pearl, Bayesian networks are directed acyclic graphs in which nodes represent variables that can be read as either probabilities or degrees or beliefs and directed edges as conditional probabilities from parent to child. By the Markov convention, the value of the node is independent of the other nodes that are not its descendants conditional on its parents. Changes of values at the nodes of a Bayesian network in response to evidence, for example, are updated through belief propagation algorithms applied at every node. The update of a response to an input from a parent uses conditional probabilities of the link. A parent's response to the input from a child uses the related likelihood ratio. Reading some variables as hypotheses and others as pieces of evidence, simple instances of core scientific concepts can easily be read off such a structure. Simple explanation accounts to showing how the value of a variable downstream depends on the pattern upstream. Simple confirmation amounts to an increase in the probability or degree of belief of a node upstream given the pieces of evidence downstream. Evaluating competing hypotheses consists in calculating the comparative probability of different patterns upstream. One clear reading of networks is as causal graphs. As Pearl notes, a Bayesian network is nothing more than a graphical representation of a huge table of joint probabilities for the variables involved. Given any sizable number of variables, however, calculation becomes humanly unmanageable, hence the crucial use of computers. The fact that Bayesian networks are also computationally intensive is in fact, a point the guard makes against using them as models of human cognitive processing, but that is not an objection against other philosophical interpretations. Application to philosophical questions of causality and philosophy of science is detailed in Spurt's, Glymer and Shanes, and Spranger and Hartman. Bayesian networks are now something of a standard in artificial intelligence, ubiquitous in its applications, and powerful algorithms have been developed to attract causal networks from the massive amounts of data available. Network models of scientific communication. It should be no surprise that the computational studies of belief change and opinion dynamics noted above blend smoothly into a range of computational studies in philosophy of science. Here, a central motivating question has been one of optimal investigatory structure. What patterns of scientific communication and cooperation between what kinds of investigators is best positioned to advance science? There are two strands of computational philosophy of science that attempt to work towards an answer to this question. The first strand models the effect of communicative networks within groups. The second strand, left to the next section, models the effect of cognitive diversity within groups. This section outlines what makes modeling of both sorts promising, but also notes limitations and some failures as well. One might think that access to more data by more investigators would inevitably optimize the truth-seeking goals of communities and investigators. On that intuition, faster and more complete communication, the contemporary science of the internet would allow faster, more accurate, and more exploration of nature. Surprisingly, however, the first strand of modeling offers robust arguments for the potential benefits of limited communication. In the spirit of rational choice theory, much of the work was inspired by analytical work in economics on infinite populations by Venkatesh Bala and Sanjeev Goyal, 1998, computational implemented for small populations in a finite context with an eye to philosophical implications by Kevin Zollman. In Zollman's model, Bayesian agents choose between the current method and what is set as a better method, starting with random beliefs and allowing agents to pursue the investigatory action with the highest subjective utility. Agents update their beliefs based on the results of their own testing results drawn from the distributions for that action together with the results from the other agents to which they are communicatively connected. A community is taken to have successfully learned when all the agents converge on the better method. Olson and Angary's Bayesian network Lupata has also been applied to the question of optimal networks for scientific communication. Their results essentially confirm Zollman's result, though sampled over a larger range of networks. Distributed networks with low connectivity are those that most reliably fix on the truth, though they are not bound to do so more slowly. The concept of an epistemic landscape has also emerged as of central importance in this strand of research, analogous to the fitness landscape in biology. An epistemic landscape offers an abstract representation of ideal data that might in principle be obtained in testing a range of hypotheses. An epistemic landscape is intended to be an abstract representation of the real-world phenomenon being explored. The key word, of course, is abstract. Few would argue that such a model is fully realistic, either in terms of the simplicity of limited dimensions or the precision in which one hypothesis has a distinctly higher value than a close neighbor. As in all modeling, the goal is to represent as simply as possible those aspects of a situation relevant to answering a specific, in this case, the question of optimal scientific organization. Epistemic landscapes, even those this simplistic, have been assumed to offer a promising start. As outlined below, however, one of the deeper conclusions that has emerged is how sensitive results can be to the specific topography of the epistemic landscape. Is there a form of scientific communication which optimizes its truth-seeking goals in exploration of the landscape? In a series of agent-based models, agents are communicatively linked explorers situated at specific points in epistemic landscape. In such a design, simulations can be used to explore the effect of a network structure, the topography of the epistemic landscape, and the interaction of the two. The simplest form of the results echo the patterns seen in different forms of Bala and Goyle and in Zollman, here played out on epistemic landscapes. Agents start with a random hypothesis as points on the x-axis of a two-dimensional landscape. They compare the results, the height of the y-axis at that point, with those of the other agents to which they are networked. If the network neighbor has a higher result, the agent moves towards an approximation of that point with an inertia factor. This process is repeated by all agents, progressively exploring the landscape and attempting to move towards more successful results. What all these models suggest is that it is a distributed network of communication between investigators, rather than a full and immediate communication between all that will, or at least can, give us more accurately scientific outcomes. In the 17th century, scientific results were exchanged slowly from person to person in the form of individual correspondence. In today's science, results are instantly available to everybody. What these models suggest is that the communication mechanisms of the 17th century science may be more reliable than the highly connected communication of today. Zollman draws this corollary conclusion that loosely connected communities made up of less informed scientists might be more reliable in seeking the truth than communities of more informed scientists that are better connected. The explanation is not far to seek. In the models noted, more connected networks produce inferior results because agents move too quickly to salient but suboptimal positions, too local rather than global maxima. In the landscape model surveyed, connected networks result in all investigators moving towards the same points, currently announced to everybody as highest, skipping over large areas in the process precisely where the needle in the haystack might be hidden. In more distributed networks, local action resulted in far more even an effective exploration of widespread areas of the landscape, exploration rather than exploitation. How should we structure the funding and communication structure of our scientific communities? It is clear both from these results in the current form and the further work along these general lines that the answer may well be landscape relative. It may well depend on what kind of question is at issue, what form scientific communications ought to take. It may also depend on what desiderata are at issue. These models surveyed emphasize accuracy of results abstractly modeled. All of those surveyed concede that there are clear trade-off between accuracy of results and the speed of community consensus. But for many purposes and reasons, both ethical and practical, it may often be far better to work with a result that is only roughly accurate but available today than to wait 10 years for a result that in many times is more accurate but arrives far too late. Division of labor, diversity, and exploration. A second tradition of work in the computational philosophy of science also uses epistemic landscapes, but attempts to model the effect not of network structure, but of the division of labor and the diversity within the scientific community. An influential but ultimately flawed precursor in this tradition is the work of Weisberg and Muldoon in 2009, and their treatment points on the base plane of the landscape represent approaches, abstract representations of the background theories, methods, instruments, and techniques used to investigate a particular research question. Heights at those points are taken to represent scientific significance. The agents that traverse this landscape are not networked, as in the earlier studies noted, except to the extent that they are influenced by agents with approaches near theirs on the landscape. What is significant about the Weisberg and Muldoon model, however, is that their agents are not homogeneous. Two types of agents play a primary role. Followers take previous investigations of the territory by others into account in order to follow successful trends. If any previously investigated points in their immediate neighborhood have a higher significance than the point they stand on, they move to that point, randomly breaking any tie. Only if no neighboring investigated points have higher significance and uninvestigated points remain, followers move to one of those. Mavericks avoid previously investigated points much as followers prioritize them. Mavericks choose unexpected points in their neighborhoods, testing significance. If higher than their current spot, they move to that point. Weisberg and Muldoon measure both the percentages and runs in which groups of agents find the highest peak and the speed at which peaks are found. They report that the epistemic success of a population of followers is increased when mavericks are included, and that the explanation for the effect lies in the fact that mavericks can provide pathways for followers. Mavericks help many of the followers to get unstuck and to explore more fruitful areas in the epistemic landscape. Against that background, they argue for broad claims regarding the value for an epistemic community of combining different research strategies. The optimal division of labor that their model suggests is a healthy number of followers with a small number of mavericks. Critics of the model do not deny the general conclusion that Weisberg and Muldoon draw, that cognitive diversity or division of cognitive labor can favor social epistemic outcomes. What they deny is that Weisberg and Muldoon's model adequately supports that conclusion. A particularly intriguing model that does support that conclusion, built on a very different model of diversities that Hong and Page 2004, but it also supports a point that Alexander emphasized, that the advantage of cognitive diversity can very much depend on the epistemic landscape being explored. What Hong and Page demonstrate in simulation is that groups with random heuristics routinely outperform groups composed entirely of the best individual performers. They question their findings, the diversity trumps ability result. The Hong-Page model solidly demonstrates a general claim attempted in the disputed Weisberg-Muldoon model. Cognitive diversity can indeed be a social epistemic advantage in application. However, the Hong-Page result has sometimes been appealed to as a support for the much broader claims that diversity is always or quite generally of epistemic advantage. The result itself is limited in ways that have not always been acknowledged, in particular proves sensitive to the precise character of the epistemic landscape employed. Grimm 2009 expands the Hong-Page model to incorporate other landscapes as well, in which challenge the general conclusions regarding diversity that have been drawn from the model, but which also suggest the potential for further interesting applications. The Hong-Page result is therefore very sensitive to the smoothness of the epistemic landscape modeled. This is an indication from within the modeling tradition itself of the dangers of restricted and oversimple abstractions regarding epistemic landscapes. Moreover, the model's sensitivity is not limited to landscape smoothness. Social epistemic success depends on the pool of numbers from which heuristics are drawn as well, with diversity showing strength on smoother landscapes if the pool of heuristics is expanded. Results also depend on Whether social interactions is modeled using Hong page relay or an alternative dynamics in which individuals collectively rather than sequentially announce their results, with all moving to the highest point announced by any. Different landscape smoothnesses, different heuristic pool size, and different interactive dynamics will favor the epistemic advantage of different compositions of groups with different proportions of random and best performing individuals. AKL just black tea. Um, Ethics and social political philosophy. What then is the conduct that ought to be adopted, the reasonable course of conduct from this egoistic, naturally unsocial being living side by side with similar beings? Henry Singwick, The Outlines of the History of Ethics, 1866. Hobbes' Leviathan can be read as asking with Sidgwick how cooperation can emerge in a society of egoists. Cooperation is thus a central theme in both ethics and social political philosophy. Game theory and the evolution of cooperation. Game theory has been a major tool in many of the philosophical considerations of cooperation, extended with the computational methodologies. Here, the primary example is the prisoner's dilemma, a strategic interaction between two agents with a payoff matrix in which joint cooperation gets a higher payoff than joint defection, but the highest payoff goes to a player who defects when the other player cooperates. It is clear in the one-shot prisoner's dilemma that defection is strictly dominant. Whether the other player cooperates or defects, one gains more points by defecting. But if defection always gives a higher payoff, what sense does it make to cooperate? In a Hobbesian population of egoists with payoffs as in the prisoner's dilemma, it would seem that we should expect mutual defection as both a matter of course and the rational outcome. Hobbes' war of all against all. How could a population of egoists come to cooperate? How could the ethical desideratum of cooperation arise and persist? A number of mechanics have been shown to support the emergence of cooperation: kin selection, green beards, secret handshakes, iterated games, spatialized and structured interactions, and noisy signals. This section offers examples of the last two of these. In the iterated prisoner's dilemma, players repeat their interactions either in a fixed number of rounds or an infinite or indefinite repetition. Robert Axelrod's tournaments in the early 1980s are the classic studies in the iterated prisoner's dilemma and earlier examples of the application of computational techniques. Strategies for playing the prisoner's dilemma were solicited from experts in various fields, pitted against all others and themselves in round-robin competitions over 200 rounds. Famously, the strategy that triumphed was tit for tat, a simple strategy which responds to cooperation from the other players on the previous round, with cooperation responding to a defection on the previous round with defection. Even more surprising, tit for tat again came out in front in a second tournament, despite the fact that submitted strategies knew that tit for tat was the opponent to aim for. When those same strategies were explored with replicator dynamics in place of round robin competition, tit for tat again was the winner. Further work has tempered tit for tat's reputation somewhat, emphasizing that constraints of Axelrod's tournaments, both in terms of structure and strategies submitted. There are two aspects of the emergence of cooperation in the form of tit for tat. One is the fact that play is local. Strategy total points over just local interactions rather than plays with all other cells. The other is that imitation is local as well. Strategies imitate their most successful neighbor rather than the strategy in the raid that gain the most points. The fact that both conditions play out in the local structure of the lattice allows clusters of tit for tat to form and grow. In Axelrod's tournament, it is particularly important that tit for tat does well in play against itself. The same is true here. If either game interaction or strategy updating is made global rather than local, dominance goes to all defect instead. One way in which cooperation can emerge, then, is through structured interactions. Axelrod offers particularly thorough investigation of different interaction structures and different games. Martin Nowak and Carl Sigmund offer a further variation that results in even more surprising level of cooperation in the prisoner's dilemma. The reactive strategies outlined above are communicatively perfect strategies. There's no noise in hearing a move as cooperation or defection on the other side, and no shaking hands in response. And tit for tat, a cooperation on the other side is flawlessly perceived as such For example, and is perfectly responded to with cooperation. If signals are noisy or responses are less than flawless, however, tit for tat loses its advantage in play against itself. In that case, a chancy defection will set up a chain of mutual defections until a chancy cooperation reverses a trend. A noisy tit for tat played against itself in an infinite game does no better than a random strategy. Nowak and Sigmund replace the perfect strategies with uniformly stochastic ones reflecting a world of noisy signals and actions. The closest to alt effect will now be a strategy of zero point zero 0.01 or and so on, indicating the strategy has only a 99% chance of defecting initially, and in response to either cooperation or defection, the closest to tit for tat will be a strategy of 0.99, 0.99, and 0.01, indicating merely a high probability of starting with cooperation and responding to cooperation with cooperation, defection with defection. Using the mathematical fiction of an infinite game, Nowak and Sigmund are able to ignore the initial value, pitting a full range of stochastic strategies of this type against each other in a computerized tournament using replicator dynamics in a matter of Axelrod and Hamilton. Nowak and Sigmund trace a progressive evolution of strategies. Computer simulation shows imperfect alt effect to be an early winner, followed by imperfect tit for tat. But at that point, dominance in the population goes to a still more cooperative strategy, which cooperates with cooperation 99% of the time, but cooperates even against defection 10% of the time. That strategy is eventually dominated by one that cooperates against defection 20% of the time, and then by one that cooperates with defection 30% of the time. Nowak and Sigmund show analytically that the most successful strategy in a world of noisy information will be generous tit for tat. How can cooperation emerge in a society of self-serving egoists? In the game theoretic context of the prisoner's dilemma, the results indicate that iterated interaction, spatialized and structural interaction, and noisy information can all facilitate cooperation, at least in the form of strategies such as tit for tat. When all three effects are combined, the results appear to be a level of cooperation even greater than that indicated in Nowak and Sigmund. This outline is focused on some basic background regarding the prisoner's dilemma and emergence of cooperation. More recently, a generation of richer game theoretic models has appeared using a wider variety of games and conflict and coordination, and more closely tied to historical precedents in social and political philosophy. Newer game theoretical analysis, state of nature scenarios, and Hobbes appeared in van der Schraff in 2006 and Chung in 2015, extended with simulations to include Locke and Nozick in Brunner. There is also a new body of work that extends game theoretic modeling and simulation to questions of social inequity. Brunner 2017 shows that the mere fact that one group is a minority in a population and thus interacts more frequently with the majority than with minority members can result in its being disadvantaged where exchanges are characterized by bargaining in a Nash demand game. Termed the cultural red king, the effect has been further explored through simulation with links to experiment and with extensions to questions of intersectional disadvantage, in which overlapping minority categories are in play. The relevance of this to the focus of previous section is made clear in Rubin and O'Connor and Brunner 2019, Modeling Minority Disadvantage in Scientific Communities. Modeling democracy. In computational simulations, game theoretic cooperation has been appealed to as a model for aspects of both ethics in the sense of Sidgwick and in social political philosophy on the model of Hobbes. That model is tied to game theoretical assumptions in general, however, and often to the structure of the prisoner dilemma in particular. With regard to a wider range of questions in social and political philosophy in particular, the limitations of game theory may seem unhelpfully abstract and artificial. While still abstract, there are other attempts to model questions in social political philosophy computationally. Here, the studies mentioned earlier regarding polarization are relevant. There have also been recent attempts to address questions regarding epistemic democracy, the idea that among its other virtues, democratic decision-making is more likely to track the truth. There is a contrast, however, between open democratic decision-making in which full population takes place and representative democracy in which decision-making is passed up through a hierarchy of representation. There is also a contrast between democracy seen as purely a matter of voting and a deliberative process that in some way involves the population in wider discussion. The classic result from open democracy and simple voting is the Condorcet jury theorem. As long as each voter has a uniform and independent probability greater than 0.5 of getting an answer right, the probability of correct answer for a majority vote is significantly higher than that of any individual, and it quickly increases with the size of the population. It can be shown analytically that the basic thrust of the Condorcet result remains when assumptions regarding uniform and independent probabilities are relaxed. The Condorcet result is significantly weakened, however, when applied in hierarchical representation in which smaller groups first reach a majority verdict, which is carried to a second level of representatives who use a majority vote on that level. More complicated questions regarding deliberative dynamics and representation require simulation using computers. The Hong-Page structure of group deliberations outlined in the context of computational philosophy of science above can also be taken as a model of deliberative democracy beyond a simple vote. The success of deliberation in a group can be measured as the average value height of points found in a representative instantiation of this kind of deliberation. Smaller groups of individuals first use their individual heuristics to explore a landscape collectively, then handling their collective best for each point on the landscape to a representative. In a second round of deliberation, the representatives work from the results from their constituents in a second round of exploration. Unlike in the case of pure voting and the Condorcet results, computation and simulation show that the use of representative structure does not dull the effect of deliberation on this model. Results like these show how computational models might help expand the political philosophical arguments for representative democracy. Social and political philosophy appears to be a particularly promising area for big data and computational philosophy employing the data mining tools of computational social science, but as of this writing, the development remains largely a promise for the future. Social outcomes of complex systems. The guiding idea of interdisciplinary theme known as complex system is that phenomena on a higher level can emerge from complex interactions on a lower level. The emergence of social outcomes from the interaction of individual choice is a natural target, and agent-based modeling is a natural tool. Opinion polarization and the evolution of cooperation outlined above both fit this pattern. A further classic example is the work of Thomas Schelling on residential segregation. A glance at demographic maps in American cities make the fact of residential segregation obvious. Ethnic and racial groups appear to clearly distinguish patches in this open and shut indication of rampant racism in American life. Schelling attempted to answer this question with an agent-based model that originally consisted of pennies and dimes on a checkerboard array, but which has been studied computationally in a number of variations. Two types of agents are distributed at random across a cellular automata lattice with given preferences regarding their neighbors. In its original form, each agent has a threshold regarding neighbors of their own kind. At that threshold level and above, agents remain in place. Should they not have that number of like neighbors, they move to another spot. In some variation, a move at random. In others, a move to the closest spot that satisfies their threshold. What Schelling found was the residential segregation occurs even without a strong racist demand that all of one's neighbors, or even most, are of one's kind. Even when preference is just a third of one's neighbors are of one's kind, clear patches of residential segregation appear. The conclusion that Schelling is careful to draw from such a model is simply that a low level of preference can be sufficient for residential segregation. It does not follow that more egregious social and economic factors aren't operative or even dominant in the residential segregation we actually observe. In this case, basic modeling assumptions have been challenged on empirical grounds. Elizabeth Bruch and Robert Mayer used sociological data on racial preferences, challenging the sharp cutoff employed by Schelling's model. They claim on the basis of simulation that Schelling's effect disappears when more realistically smooth preference functions are used instead. Their simulations and the latter claim turn out to be an error, but the example of testing the robustness of simple models with an eye to real data remains a valuable one. Computational philosophy of language. Computational modeling has been applied in philosophy of language along two main lines. First, there are investigations of analogy and metaphor using models of semantic webs that share a developmental history with some of the models of scientific theory outlined above. Second, there are investigations of the emergence of signaling which have used a game theoretical base akin to some approaches to the emergence of cooperation discussed above. Semantic web, analogy, and metaphor. WordNet is a computerized lexical database for English built by George Miller in 1985 with a hierarchical structure of semantic categories intended to reflect empirical observations regarding human processing. There is a long tradition across psychology, linguistics, and philosophy in which analogy and metaphor are seen as important key to abstract reasoning and creativity. Beginning in the 1980s, several notable attempts have been made to apply computational tools in order to both understand and generate analogies. Douglas Hofstadter and Melanie Mitchell's Copycat, developed as a model of high-level cognition, has codelets compete within a network in order to answer simple questions of analogy. Holyoake and Thagard envisage metaphors as analogies in which the source and target domain are semantically distinct, calling for a relational comparison between two semantic necks. In the Holyoake and Thagard model, those comparisons are constrained in a number of different ways that call for coherence. Their computational modeling for coherence, in the case of metaphor, was in fact direct ancestor to Thagard's coherence modeling of scientific theory change discussed above. Eric Steinhardt and even Eva Kidde's NetMet offers an illustration of the relational approach to analogy and metaphor. They use one semantic and inferential subnet related to birth, another related to the theory of ideas in the Theaetetus. Each subnet is characterized in terms of relations of containment, production, discarding, helping, passing, expressing, and opposition. On that basis, NetMet generates metaphors. NetMet can be applied to large linguistic databases such as WordNet. Signaling games and the emergence of communication. Suppose we start without pre-existing meanings. It is possible that under favorable conditions, unsophisticated learning dynamics can spontaneously generate meaningful signaling. The answer is affirmative. Ryan Skirms and Signals. David Lewis's sender-receiver game is a cooperative game in which senders observe a state of nature and choose a signal. A receiver observes that signal and chooses an act, with both sender and receiver benefiting from an appropriate coordination between state of nature and act. A number of researchers have explored both analytic and computational models of signaling games with an eye to ways in which initially arbitrary signals can come to function in ways that start to look like meaning. Communication can be seen as a form of cooperation, and here, as in the case of emergence of cooperation, the methods of communicative strategy change seem less important than the interactive structure in which those strategies play out. Computer simulations show the simple imitation of a neighbor's successful strategy. Various forms of reinforcement learning and training up of simple neural nets on successful neighbors' behaviors can all result in the emergence and spread of signaling systems, sometimes with different dialects. Development on a cellular autonomous grid produces communication with any of these techniques, even when the rewards are one-sided rather than mutual in strict Lewis signaling game. But structures of interaction that facilitate communication can also co-evolve with the communication they facilitate as well. Elliot Wagner extends the study of communication on interaction structures to other networks as well. On interpretation in terms of biological evolution, computationally emergent signaling of this sort can be seen as modeling communication in vervet monkeys, or even chemical signals in bacteria. If interpreted in terms of learned culture, particularly with an eye to more complex signal combination, these have been offered as models of mechanisms at play in the development of human language. From theorem provers to ethical reasoning, metaphysics, and philosophy of religion. Many of our examples in computational philosophy have been examples of simulation, often social simulation by way of agent-based modeling. But there is also a strong tradition in which computation is used not in simulations, but as a way of mechanizing and extending philosophical argument, typically understood as deductive proof, with an application in philosophy of logic and ultimately in deontic logic, metaphysics, and philosophy of religion. Entitling a summer Dartmouth conference in 1956, the organizers coined the term artificial intelligence. One of the higher points of the conference was a computational program for the construction of logical proofs developed by Alan Newell and Herbert Simon at Carnegie Mellon and programmed by Shaw using the vacuum tubes of the Joniac computer at the Institute for Advanced Study. Newell and Simons, the logical theorist, was given 32 theorems from a chapter of Whitehead and Russell's Principia Mathematica, of which he successfully proved 38, including a proof more elegant than the one Whitehead and Russell's own. Russell himself was impressed. I'm delighted to know that Principia Mathematica can now be done by machinery. I'm quite willing to believe that everything in deductive logic can be done by machinery. Despite possible claims to anticipation, the most compelling of which may be Martin Davis's 1950 computer implementation of Maschwez Pressburger's decision procedure for a fragment of arithmetic, the logical theorist is standardly regarded as the first automated theorem prover. Newell and Simon's target, however, was not so much a logic prover as a proof of concept for an intelligent or thinking machine. Having rejected geometric proofs as too reliant on diagrams and chess as too hard, by Simon's own account, they turned to logic because Principia Mathematica happened to be on his shelf. Simon Newell's primary target was not an optimized theorem prover, but a thinking machine that in some way matched human intelligence. They therefore relied on heuristics thought of as matching human strategies, an approach later ridiculed by Hua Wang. There is no need to kill a chicken with a butcher's knife, yet in the net impression is that Newell saw Simon failed even to kill the chicken, to argue the superiority of heuristics over algorithmic methods by choosing a particular inefficient algorithm seems hardly just. Later theorem provers were focused on proof rather than a model of human reasoning. By 1960, Hao Wang, Paul Gilmore, and Doc Prowitz had developed computerized theorem provers for the full first-order predicate calculus. In the 1990s, William McCune developed Otter, a widely distributed and accessible prover for first-order logic. Theorem provers developed for higher-order logics working from a variety of approaches. With clever implementation and extension, these also allowed automation of aspect of modal, deontic, epistemic, intuitionist, and paraconsistent logics of interest both in their own terms and in application within computer science, robotics, and artificial intelligence. Within pure logic, Portaro lists a number of results that have been established using automated theorem provers. It was conjectured for 50 years that a particular equation in a Robbins algebra could be replaced by a simpler one. For example, even Tarski had failed in an attempt at proof, but McCune produced an automated proof in 1997. Shortest and simplest axiomizations for implicational fragments of the modal logic S4 and 5 had been studied for years as open questions with eventual results by automated reasoning in 2002. Theorem provers has been applied with deontic logics in the attempt to mechanize ethical reasoning and decision-making. Alan Gurwith has argued that agents contradict their status as agents if they don't accept a principle of generic consistency, respecting the agency necessary rights of others as a supreme principle of practical rationality. Funmeyer and Benzmuller have shown that even an ethical theory of this complexity can be formally encoded and assessed computationally. One of the major advances in computational philosophy has been the application of theorem provers to the analysis of classical philosophical positions and arguments. For axioms of metaphysical object theory, Zoltan and his collaborators used Prover 9 and Mace to establish theorems regarding possible worlds, such as the claim that every possible world is maximal, modal theorems in Leibniz, and consequences from Plato's theory of forms. Versions of ontological argument have been formed in important thread in recent work employing theorem provers both because of their inherent interest and the technical challenge they bring with them. Prover 9 and Mace have again been used recently by Jack Horner in order to analyze a version of ontological argument in Spinoza's Ethics and to propose an alternative. Significant work has been done on versions of Anselm's ontological argument. Christopher Benzmuller and his colleagues have applied a higher order theorem prover, including Isabel Hole and their own Leo 2 and 3, in order to analyze the version of ontological argument found in the papers of Kurt Gödel. A previous unnoticed inconsistency was found in Gödel's original, though avoided in Dana Scott's transcription. Theorem provers confirmed that Gödel's argument forces modal collapse. All troops become necessary troops. Analysis within theorem provers make it clear that variations proposed by Anthony Anderson and Melvin Fitting avoid that consequence, but in importantly different ways. Work in metaphysics employing theorem provers continues. Here, of particular note is Ed Zolta's ambitious and long-term attempt to ground metaphysics quite generally in computationally instantiated object theory. Artificial Intelligence and Philosophy of Mind. The Dartmouth Conference of 1956 is standardly taken as marking the inception of both the field and the term artificial intelligence. There were, however, two distinct trajectories apparent in that conference. Some of the participants took as their goal to be the development of intelligent or thinking machines, with perhaps an understanding of human processes as a begrudging means to that end. Others took their goal to be a philosophical and psychological understanding of human processing, with the development of machines a means to that end. Those in the first group were quick to exploit linear programming, what came to be known as GOFI, or good old-fashioned artificial intelligence. Those in the second group rejoiced when connectionist and neural net architectures came to maturity several decades later, promising models directly built on and perhaps reflective of mechanisms in the human brain. Attempts to understand perception, conceptualization, belief change, and intelligence are all part of the philosophy of mind. The use of computational models towards the end, the second strand above, thus comes close to the computational philosophy of mind. Daniel Dennett has come close to saying that AI is philosophy of mind, a most abstract inquiry into the possibility of intelligence and knowledge. The bulk of AI research remains strongly oriented towards producing effective and profitable information processing, whether or not the result offers philosophical understanding. So it is perhaps better not to identify AI with philosophy of mind, though AI has often been guided by philosophical conceptions, and aspects of AI have proven fruitful for philosophical exploration. Philosophy of AI and philosophy of mind, inspired by and in response to AI, which are not the topic here, have both been far more common than philosophy of mind developed with the techniques of AI. One example of a program in artificial intelligence that was explicitly conceived in philosophical terms and designed for philosophical ends was the Oscar project developed by John Pollock, but cut short by his death. The goal of the Oscar was construction of a computational agent, an artificial intellect. At the core of Oscar was implementation of a theory of rationality. Pollock was explicit regarding the intersection of AI and philosophy of mind in that project. The implementality of the theory of rationality is a necessary condition for its correctness. This amounts to saying that philosophy needs AI just as much as AI needs philosophy. At the core of Oscar's rationality is implementation of defeasible, non-monotonic logic employing prima facie reasons and potential defeaters. Among its successes, Pollock claims an ability to handle the lottery paradox and preface paradoxes. Informally, the fact that we know that one of the many tickets in the lottery will win means that we must treat ticket 1 will not win, ticket 2 will not win, and the like, not as items of knowledge, but as defeasible beliefs for which we have strong prima facie reasons. Pollock's formal treatment in terms of collective defeat is nicely outlined in a supplement of Oscar in Bringjord and Govind Darjula. Evaluating computational philosophy. The sections above were intended to be an introduction to computational philosophy, largely by example emphasizing both the variety of computational techniques employed and the spread of the philosophical topics to which they are applied. The final section is devoted to the problems and the prospects of computational philosophy. Critiques. Although computational instantiations of logic are of an importantly different character, simulation, including agent-based simulation, plays a major role in much of computational philosophy. Beyond philosophy across all disciplines of its application, simulation often raises suspicions. A standard suspicion of simulation in various fields is that one can prove anything by manipulation of model structure and parameters. The worry is that the anticipated or desired effect could always be backed in, programmed as an artifact in the model itself. Production of a simulation would thus demonstrate not the plausibility of a hypothesis or a fact about the world, but merely the cleverness of the programmer. In a somewhat different context, Rodney Brooks had written that the problem with simulation is that they are doomed to succeed. But consider a similar critique of logical argument that one can prove anything by careful choice of premises and rules of inference. The proper response in the case of logical argument is not to concede the fact that a derivation for any proposition can be produced from carefully chosen premises and rules, but to emphasize that it may be difficult or impossible to produce a derivation from agreed rules and clear and plausible premises. A similar response is appropriate here. The effectiveness of simulation as arguments depend on the strength of the assumptions and the soundness of its mechanisms, just as the effectiveness of logical proof depends on the strength of its premises and the validity of its rules of inference. The legitimate force of the critique, then, is not that simulation is inherently untrustworthy, but simply that the assumptions of any simulation are always open to further examination. Anyone who has attempted computer simulation can testify that it is often extremely difficult or impossible to produce an expected effect, particularly a robust effect across a plausible range of parameters and with a plausible basic mechanism. Like experiment, simulation can demonstrate both the surprising fragility of a favored hypothesis and the surprising robustness of an unexpected effect. Far from being doomed to succeed, simulations fail quite regularly in several important ways. Two standard forms of simulation failure are failure of verification and failure of validation. Verification of a model demands assuring that it accurately reflects design intention. If a computational model is intended to instantiate a particular theory of belief change, for example, it fails verification if it does not accurately represent the dynamics of that theory. Validation is perhaps the more difficult demand, particularly for philosophical computation, that the computational model adequately reflects those aspects of the real world it is intended to capture or explain. If its critics are right, a simple example of verification failure is the original Weisberg and Muldoon model of scientific exploration outlined above. The model was intended to include two different kinds of epistemic agents, followers and mavericks, with distinct patterns of exploration. Mavericks avoid previously investigated points in their neighborhood. Followers move to neighborhood points that have been investigated but have a higher significance. In contrast to their descriptions in text, the critics argue that the software for the model used a greater or equal in place of greater at a crucial place, with the result that followers move to the neighboring points with a higher or equal significance, resulting in their often getting stuck in a very local oscillation. If so, Weisberg and Muldoon's original model fails to match its design intention. It fails verification, though some of their original conclusions regarding epistemic diversity have been vindicated in further studies. Validation is a very different and more difficult demand that a simulation model adequately captures relevant aspects of what is intended to model. A common critique of specific models is that they are too simple, leaving out some crucial aspect of the model phenomenon. When properly targeted, this can be entirely appropriate critique. But what it calls for is not the abandonment of modeling, but better construction of a better model. In time, the Cartographers Guild struck a map of the empire whose size was that of the empire, and which coincided point by point with it. The following generations saw that the vast map was useless. From Borges on the Exactitude in Science, 1946. Borges' story is often quoted in illustration of the fact that no model, no scientific theory can include all characteristics of what it is intended to model. Models and theories would be useless if they did. The purpose of both theories and models is to present similar representations of mechanisms that capture the relevant features of dynamics of a phenomenon. What aspects of a phenomenon are in fact the relevant aspects for understanding the phenomenon calls for evaluative input outside of the model, but where relevant aspects are omitted, irrelevant aspects are included, or unrealistic or artificial constraints imposed. What a critique calls for is a better model. There's one aspect of validation that can sometimes be gauged at the level of modeling itself and with modeling tools alone, where the target is some general phenomenon, opinion polarization, or the emergence of communication. For example, a model which produces that phenomenon within only a tiny range of parameters should be suspicious. Our estimate is that parameters actually play in the actual phenomenon may be merely intuitive or extremely rough, and the real phenomenon may be ubiquitous in a wide range of settings. In such a case, it would seem prima facie unlike that a model which produced a parallel effect within only a tiny window of parameters could be capturing the general mechanism of a general phenomenon. In such cases, robustness testing is called for, a test for one aspect of validation that can still be performed on the computer. To what extent do conclusions drawn from the modeling effect hold up under a range of parameter variations? The Hong page model of the value of diversity in exploration outlined above has been widely appealed to quite generally as support for cognitive diversity in groups. It has been cited in NASA internal documents offered in support of diversity requirements at UCLA and appears in amicus curiae brief before the Supreme Court in support of promoting diversity in the armed forces. But the model is not robust across its several parameters, support sweepingly general claims that have been made on the basis of regarding diversity and ability or expertise. Is that a problem internal to the model or an external matter of the interpretation or application? There's much to be said for the latter alternative. The model is and remains an interesting one, interesting often in the ways in which it does show sensitivity to different parameters. Thus, a failure of one aspect of validation, robustness, with an eye to one type of general claim, can also call for further modeling intended to explore different effects in different contexts. Rosenstock, Brunner, and O'Connell, 2017, offer a robustness test for Zollman's model outlined above. Borg, Frey, Shazelia, and Straber, 2008, offer new modeling grounded precisely in a robustness critique of their predecessors. It is noteworthy that simulation failures mentioned have been detected and corrected within the literature of simulation itself. These are effective critiques within the disciplines employing simulation rather than from outside. An illustration of such a case with both verification and validation in play is that of Brook and Mayer critiquing of the Schelling segregation model and the response to it by Van Rouge, Siegel, and Macy. Many aspects of that model are clearly artificial, a limitation to two-group spatialization on a cellular automata grid, and unhappiness or moving in terms of sharp threshold cutoff of tolerance for neighbors or the other group. Brook and Mayer offered clear empirical evidence that residential preferences do not fit a sharp threshold. More importantly, they build a variation of the Schelling model in order to show that the Schelling effect disappeared with more realistic preference profiles. What Brook and Mayer challenged, in other words, was validation, not merely that aspects of the target phenomenon of residential segregation were left out, as they would be in any model, but that relevant aspects were left out, differences that made an important difference. Van der Rich, Siegel, and Macy failed to understand why the smooth preference curves in Brook and Mayer's data wouldn't support rather than defeat the Schelling effect. On investigation, they found that they would. Brook and Mayer's validation claim against Schelling was itself founded in a programmatic error. To reach Siegel and Macy, verdict was that Brook and Mayer's attack itself failed model verification. In the case of both Weisberg and Muldoon and Brook and Mayer, original code was made freely available to their critics. In both cases, the original authors recognized the problems revealed, though emphasizing aspects of the work that survived the criticism. Here again, an important point is that critiques and responses of this type have arisen and have been addressed within the philosophical and scientific simulation itself, working towards better models and practices. Prospects and underdeveloped aspects. Philosophy, at its best, has always been in contact with concepts and scientific methodologies of its time. Computational philosophy can be seen as a contemporary instantiation of that contact, crossing disciplinary boundaries in order to both influence and benefit from developments in computer science and artificial intelligence. Incorporation of new technologies and wider application within philosophy can be expected and should be hoped for. There is one extremely promising area in need of development within computational philosophy, though that area may also call for changes in conceptions of philosophy itself. Philosophy has classically been conceived as abstract rather than as concrete, as seeking understanding at the most general level rather than specific prediction or retrodiction, often normative, and as operating in terms of logical argument and analysis rather than empirical data. The last of these characteristics, and to some extent the first, will have to be qualified if computational philosophy grows to incorporate a major batch of contemporary techniques, those related to big data. Expansion of computational philosophy in the intersection with big data seems an exciting prospect for social and political philosophy in the analysis of belief change and in understanding the social and historical dynamics of philosophy of science. A particular benefit would be better prospects for validation of a range of simulations and agent-based models, as emphasized above. If computational philosophy moves in that promising direction, however, it may take a more empirical character in some respects. Emphasis on general and abstract understanding and concern with the normative will remain marks of a philosophical approach, but the membrane between some topic areas in philosophy and aspects of computational science can be expected to become more permeable. Dissolving these disciplinary boundaries may itself be good in some respects. The examples presented above make it clear that in incorporating and contributing to computational techniques developed in other areas, computational philosophy has long been cross-disciplinary. If our gain is a better understanding of these topics that have long fascinated us, compromise in disciplinary boundaries and a change in our concept of philosophy seem a small price to pay. Okay, so God bless. There you have it, the completion of all of the things I wanted to cover for my introduction to the philosophy of science. Obviously, the topic is endless and could go on forever and ever, but that will have to suffice for my purposes here. And for the multiple truth hypothesis, hopefully, moving forward, you could see, especially in the computational philosophy, some of these concepts, what I'd mentioned, like a truth discovery function. What would truth look like? What would it look like if the computer were to try to investigate truth? And so hopefully you're having done this and then moving into the metaphysics series, I will start formally presenting the multiple truth hypothesis. And you look forward to things like slideshows and PowerPoints. You're like having done the due diligence and reading this out, and hopefully, moving forward, instead of just long reading, I will be able to condense this, organize my own thoughts in my own head, start making PowerPoints, writing articles. But I had to do the due diligence. So anyone who's sat through with me, you appreciate that. Hope this has been useful to you. Memes, KL, Rune, people have been there. Reiner supporting me along the way. Appreciate it. My old friend Laser Cone, good to hear from you. So if you reach out or you contact in some way, you look forward to getting back in touch. We were good friends for many years in Brooklyn and Manhattan. So good to hear from you. And from here, I will try to move into my series on metaphysics. And to some extent, it might have made more sense to do the metaphysics first. But, said that metaphysics is really like a forgotten wisdom and very esoteric. And like philosophy of science is also like that, where you mentioned people don't appreciate the need for it. But at least philosophy of science, like people, everyone thinks they know science or uses science. Most people think metaphysics has no practical purpose. So I thought I'd start with the philosophy of science, which at least people think is useful and they think that they know, as opposed to metaphysics. Most people don't even have any value of metaphysics. Not only they don't know it, they don't care about it, they think it has no value. So let me just briefly show, I have a whole folder of like 30 things for metaphysics and epistemology. I'll start with just the Wikipedia in the first episode to get the overview of the various aspects of metaphysics, ontology, identity and change, space and time, causality, possibility, mind and matter, determinism, free will, relation to science, theology, logic. You look at the long school of history, and then we'll also look at epistemology and the central concepts: knowledge, a priori and posterior knowledge, belief, truth, justification, internalism and externalism, the problem of defining knowledge, the value problem, acquiring knowledge, the regress problem, the various schools of thought: empiricism, rationalism, skepticism, pragmatism, more. And then there's a whole bunch of adjunct topics that will we'll go back to Platonic forms, the nature of math and logic, things like grounding, emergent properties, the laws of nature, hermeneutics, cause and effect, and to a formal look at the important concepts of dualism and monism, which is a topic that is very important for the multiple truth hypothesis. So it's possible, I have my act together, that I'll be ready with that next week. Wednesday, we'll continue the Wednesday afternoon series, and it'll be a lot of reading, due diligence, or it might take a few weeks. And hopefully over the next few months I'll finish that. Maybe I'll try to put a presentation or active inference. I'll start trying to put slides together and a formal framework. You see, the multiple truth hypothesis will come from multiple levels. And so there'll be a metaphysical framing, but there will also be, within the philosophy of science, a statistical formulation, computational philosophy for computer algorithms, truth discovery functions, and memory techniques related to philosophy of mind, and just as a method to working with multiple conflicting theories, or multiple, the inference to the best explanation and other things. So God bless anyone who watched my series. Hope you gain from it. Appreciate your feedback. And there's not many people out there really interested in this topic, so that's why I'm rambling. And maybe someone will see this, someone will find this, and we'll create a little community. And I did the due diligence, so as I work through these ideas, formulate them better, hopefully I will provide some better content in the future. So with that, God bless. Signing off. Best wishes. We'll see you Sunday night in Week in Review. And then hopefully maybe next week, or starting over the next few weeks, we'll be moving into the Wednesday afternoon Metaphysics and Epistemology series. So signing off. God bless.